Hello there, and welcome to Physics with William, where curiosity gets cozy and science takes the scenic route to slumber. Tonight, we're going to drift toward one of the most powerful dreams in modern science, the dream of building a tiny star on Earth, not in the sky, not safely far away across millions of miles, but here, inside a machine made by human hands. It sounds almost like something from an old science fiction story. A chamber full of glowing plasma, magnetic fields wrapped around it like invisible ropes, hydrogen heated until it becomes something wild and bright. And somewhere around all of that, a wall, a real wall, made of real matter, trying to stand calmly between an artificial star and the rest of the world. That wall is not dramatic in the way flames are dramatic. It does not glow in the imagination quite as brightly as the plasma itself. It does not get as much attention as the promise of clean energy or the idea of power plants that could run on tiny amounts of fuel. But in many ways, that wall may be one of the hardest parts of the whole dream. Because making fusion happen is not just about lighting the fire, it is about holding the fire. It is about asking ordinary matter to survive next to something that does not behave like ordinary fire at all. A candle flame can burn your finger, a furnace can melt metal. But fusion plasma is stranger than both. It is a hot, restless soup of charged particles, hotter than the centre of the sun in some ways, moving, twisting, pulsing, and looking for any weakness in the cage built around it. It cannot touch the wall for long, because if it does, the wall is damaged and the plasma cools. It cannot simply be poured into a container like tea into a mug, because the mug would not last very long, and the tea, to put it mildly, would be a little too energetic. So tonight, we're not only talking about infinite energy, or nearly infinite energy, or the long human hope of turning the same process that powers the stars into a steady source of electricity. We're talking about the final barrier between that hope and reality, the inner surface of the machine, the first solid thing that faces the storm, the part that has to endure heat, radiation, flying particles, unstable plasma, and the strange job of helping to create more fuel while also trying not to fall apart. It is a bit like asking an umbrella to survive inside a thunderstorm, while also collecting the lightning, filtering the rain, and politely making more clouds. Before we go deeper into that glowing machine, I would love to know where in the world you are listening from tonight. Are you somewhere quiet and dark, with a cup of tea nearby, or are you in the middle of a busy day, letting the soft machinery of physics keep you company for a while? And here is a fitting question for this particular journey. If humanity could really learn how to hold a star on Earth, what would that future feel like where you are? Would it feel like cleaner cities, cheaper power, quieter skies, or simply the relief of knowing that one of our oldest energy problems had finally become a little less heavy? If you find this kind of gentle science soothing, or if you enjoy letting big questions settle slowly instead of rushing past them, I would be very grateful if you gave the video a like and maybe subscribed. It helps this calm little corner of the universe reach others who might want to fall asleep with plasma, stars, magnets, and a few very patient atoms for company. And do not worry if the idea of fusion sounds complicated. Tonight we will move slowly. No need to hold every detail tightly. You can let the ideas pass through, one by one, like quiet sparks behind closed eyes. To understand why the wall of a fusion reactor matters so much, it helps to begin with the promise that made people chase fusion in the first place. All around us, energy is usually won by breaking things apart or burning things up. Coal is burned, gas is burned, oil is burned. Even in nuclear fission, heavy atoms are split apart, releasing energy from the breaking of the nucleus. Fusion is different. Fusion is not about splitting heavy atoms. It is about joining light ones. It is the process that makes stars shine. Deep inside the sun, light atomic nuclei are pressed together under immense heat and pressure, and when they fuse, a little bit of their mass is transformed into energy. That energy slowly works its way outward, through layers of solar material, until some of it arrives here as sunlight, warming oceans, feeding plants, and making afternoons feel just a little more golden. On Earth, we cannot copy the sun exactly. The sun is a luxury we do not have. It is enormous. Its own gravity squeezes its core with a pressure so vast that fusion can happen steadily across immense volumes. A fusion reactor on Earth does not have that kind of gravity. We cannot build a machine the size of a star, which is probably for the best, since parking would become difficult. Instead, scientists try to make up for the missing pressure by heating the fuel to astonishing temperatures. The fuel becomes plasma, a state of matter where electrons are stripped away from atomic nuclei, leaving charged particles moving freely. Plasma is not quite a gas in the ordinary sense. It responds strongly to electric and magnetic fields. It can form waves, currents, filaments, and sudden instabilities. It is alive with motion, though not alive in the biological sense. More like a crowd that has forgotten where the exits are and is now moving in every direction at once. The most common dream for practical fusion uses heavy forms of hydrogen. These forms are called deuterium and tritium. Deuterium can be found in seawater. Tritium is much rarer and more difficult, which will become important later. When deuterium and tritium fuse, they release energy in the form of fast-moving particles. Some of that energy stays in the plasma and helps keep it hot. Much of it is carried away by neutrons, tiny neutral particles that are not easily guided by magnetic fields, and here, quietly, the wall enters the story. Magnetic fields can hold charged particles because charged particles feel magnetic forces. That is why tokamak reactors and stellarators use powerful magnets to shape and confine plasma without letting it touch the machine directly. You can picture the plasma as a glowing ring, suspended inside a chamber, held away from the walls by carefully arranged invisible fields. But neutrons are different. They have no electric charge. They fly out of the fusion reaction like tiny messengers that do not care about the magnetic cage. They pass through the plasma, strike the surrounding materials, and deposit their energy into the reactor structure. This is useful because that energy can be captured as heat, and heat can eventually make steam, and steam can turn turbines, and turbines can make electricity. In that sense, the wall and the material behind it are not just protective shields. They are part of the power plant, but every gift has a cost. Those neutrons are fast, relentless, and damaging. When they slam into atoms in the wall, they knock them out of place. They create defects in the material. They can make the metal swell, harden, crack, or become brittle over time. They can change the chemistry of the wall by producing helium and hydrogen inside it. They can make some materials radioactive, and they do all this again and again, not as a single dramatic blow, but as a long rain of microscopic impacts. A wall inside a fusion reactor is not destroyed the way a wooden fence is destroyed by a storm. It is changed from within, atom by atom, until the solid thing you trusted is no longer quite the same solid thing. Then there is heat. Even when the plasma is kept mostly away from the wall, some energy always escapes. Some particles drift to the edge. Some waves carry energy outward. Some instabilities can suddenly push plasma toward the surface. In a fusion reactor, certain areas, especially the parts designed to handle exhaust, can face heat loads, unlike almost anything in normal engineering. Imagine designing a surface that must survive near a tiny artificial sun, then asking it to do this not for a few seconds as a laboratory demonstration, but again and again, day after day, until it becomes a reliable power station. The challenge is not only to survive once. The challenge is to survive as a machine that can work, be repaired, produce power, and make economic sense. This is where the dream of fusion becomes less like fantasy and more like very stubborn engineering. We often hear fusion described as clean energy, safe energy, the energy of the stars. All of that can be meaningful, but none of it removes the practical problem of materials. The universe may be generous with energy, but it is not gentle with surfaces. The inside of a fusion reactor asks a simple question again and again. What can you build that is close enough to a star to use its power, but strong enough not to be eaten by it? Different materials offer different answers. Tungsten is one of the favourites because it has an extremely high melting point and can stand intense heat better than many metals. It is heavy, strong and stubborn, which are good qualities when your workplace is a plasma chamber. But tungsten has its own troubles. Under neutron bombardment it can become brittle. If small amounts of tungsten enter the plasma, they can cool it down too much, because heavy atoms radiate energy very efficiently. So tungsten can survive heat, but it must not contaminate the star it is trying to contain. Beryllium has been used because it is light and can help absorb impurities in the plasma. It can also be useful in certain reactor designs, but it is toxic, which makes handling and maintenance more complicated, and it does not solve every problem of long-term durability. Boron is interesting for another reason. It can coat surfaces and help control impurities. In some machines, boron is used to condition the walls, making the plasma behave more cleanly. But boron coatings can wear away and need renewal. Liquid lithium is perhaps one of the strangest possibilities. Instead of a solid wall facing the plasma, perhaps some surfaces could use flowing liquid metal. A liquid cannot crack in quite the same way a solid can. It can absorb heat, renew itself, and interact with the plasma in useful ways. But liquid lithium brings its own puzzle box of problems. It is chemically reactive. It must be controlled, pumped, contained, and protected. It may help breed tritium, which is useful, but it also creates difficult engineering questions, and that word breeding sounds odd until you understand the fuel problem. Deuterium is abundant enough for our purposes, tritium is not. A future fusion power plant cannot simply depend on a large natural supply of tritium, because that supply does not really exist in the quantities needed for a full energy economy. So the reactor must make its own tritium. It does this by using neutrons from the fusion reaction to interact with lithium in the material surrounding the plasma. In other words, the reactor must not only contain the plasma and collect heat, it must also help produce the very fuel it needs to continue. That is a beautiful idea and a brutal engineering demand. The wall and the blanket behind it must be shield, heat collector, fuel factory and long-suffering survivor all at once. There is a quiet elegance to that. A fusion reactor is not just a fire in a bottle. It is an ecosystem of extreme physics. The plasma must stay hot enough. The magnets must hold it. The wall must endure it. The blanket must catch the neutrons. The cooling system must remove heat. The fuel system must recover and recycle tritium. Every part depends on every other part. If the plasma is too unstable, the wall suffers. If the wall sheds too many impurities, the plasma suffers. If the blanket does not breed enough tritium, the reactor cannot feed itself. If the materials become damaged too quickly, the power plant becomes impractical. Fusion is often spoken of as one big breakthrough, as if the only question is whether we can ignite the plasma. But the deeper truth is that fusion asks for many breakthroughs to happen together, and the first wall may be one of the most unforgiving. And yet, there is something deeply human about this challenge. For thousands of years, we have used fire by learning how to build boundaries around it. A campfire needed stones, a hearth needed brick, a steam engine needed a boiler, a jet engine needed alloys that could endure heat and stress. Every new source of power has required not only a flame but a vessel, not only energy but control. Fusion is the same story carried to its most extreme point. We are trying to make a star small enough to fit inside a building and obedient enough to connect to an electric grid. The barrier between success and failure may not look heroic. It may look like metal tiles, protective coatings, cooling channels, and maintenance robots. But sometimes the least glamorous parts of a dream are the ones holding the dream together. So as we begin this journey, try to picture the inside of a future fusion reactor not as a simple container, but as a place of negotiation. At the center is plasma, hot and bright and restless. Around it are magnetic fields constantly shaping and correcting. Just beyond them waits the inner wall, close enough to feel the consequences of every escape, every particle, every burst of heat. Behind that wall are layers designed to slow neutrons, capture their energy, breed fuel, and protect the rest of the machine. It is not a cage in the ordinary sense. It is more like a conversation between matter and energy, between human design and stellar behaviour. Tonight, we will follow that conversation slowly. We will begin with the promise of fusion and why it has tempted scientists for so long. Then we will move closer to the plasma itself to understand why it must be so hot, why it must be confined, and why touching the wall is such a problem. After that, we will spend time with the wall, that first barrier, and see why it faces heat, radiation, erosion, and damage unlike almost anything else we build. We will look at the strange cast of materials that might help, from tungsten to beryllium, from boron coatings to liquid lithium, each one offering a partial answer and a new set of worries. And eventually we will come to the fuel cycle, where the reactor must learn to make tritium as carefully as it burns it. For now though, just settle into the idea. Somewhere in laboratories across the world, people are trying to solve a problem that sounds almost impossible when said plainly. They are trying to build a machine that can hold a star without becoming a star itself. They are trying to make matter strong enough, clever enough, and replaceable enough to live beside a miniature sun. Not for a moment of spectacle, but for a future power plant steady and useful and calm. The final barrier to infinite energy may not be the spark. It may be the surface that survives the spark, the wall that stands closest to the brightness, and the long search for a material that can meet the fire without giving way too soon. Which brings us first to the reason this dream became so powerful in the first place, and why fusion still feels, after all these years, like the energy source waiting just beyond the edge of our reach. Fusion has always sounded a little too good to be true, which is probably why people have spent so many decades trying to make it true anyway. It promises the kind of energy that feels almost unfair compared with the fuels we have used for most of human history. A small amount of fuel, a vast amount of power, no ordinary smoke, no mountain of coal, no river of oil, no fire that has to be fed by digging deeper into the earth. It is the same basic process that lights the sun, the stars, and every clear day that has ever warmed your face. And the idea is simple enough to say in one breath. Bring light atomic nuclei close enough together, let them join, and energy comes out. Simple to say, yes. Simple to do, not quite. That is usually where fusion smiles politely and becomes one of the hardest engineering challenges humans have ever taken on. To understand why the promise is so powerful, it helps to compare fusion with the ways we already make energy. For a long time, civilization has lived by burning things. Wood, coal, oil, gas, all of them are forms of stored sunlight from the past. Plants captured sunlight. Ancient forests became buried. Heat and pressure transformed them over immense spans of time. Then humans found those stored remains, pulled them from the ground, and released their energy by burning them. There is something almost ancient about it. We found old sunlight under the earth and turned it back into fire. That fire built the modern world. It ran engines, lit cities, moved ships, warmed homes, powered factories, and made it possible for billions of people to live in ways their ancestors could hardly have imagined. But burning has a problem built into it. It creates waste in the air. It releases gases that change the climate. It depends on fuels that are unevenly distributed and politically complicated. And even when it is done carefully, it still means taking carbon that was locked away underground and putting it back into the atmosphere. Burning is powerful, but it is messy. It is useful, but not gentle. Nuclear fission changed the conversation. Instead of burning chemical fuel, fission releases energy from the nucleus of heavy atoms. It can produce enormous amounts of power without the ordinary smoke of fossil fuels. But fission also comes with difficult questions. It produces radioactive waste that must be handled and stored. It needs careful safety systems. It uses materials that raise concerns about weapons, security, and long-term responsibility. Fission is not just a machine. It is a social contract, a promise that every step will be managed with seriousness. Fusion seems to offer a different kind of bargain. Not perfect, because no real energy source is perfect, but deeply tempting. The main fuel candidates are forms of hydrogen, especially deuterium and tritium. Deuterium can be extracted from water, and water is not exactly rare on this planet. Tritium is much more difficult, and future reactors would need to make it as they operate, but the basic fuel story still feels astonishing compared with coal mines, oil fields, and gas pipelines. In fusion, the fuel is light, the energy release is huge, and the reaction does not produce carbon dioxide in the way fossil fuel combustion does. No smokestack full of ordinary combustion gases. No soot drifting into the sky. No need to burn a mountain to boil water. That is one reason fusion has become such a symbol of future energy. It seems to promise power without the familiar guilt attached to power. A way to keep lights glowing, hospitals running, homes warm, factories working, trains moving, and servers humming without adding more carbon to the air. It is not hard to see why people find this dream attractive. We're a species that likes warmth, light, comfort, refrigeration, communication, travel, and tea at unreasonable hours. Energy is not a luxury sitting off to the side of civilization. Energy is woven through almost everything we do. The question is not whether we will need energy. The question is how we can make it without damaging the conditions that let us live well. And fusion, at least in principle, seems to answer with a calm confidence that is almost suspicious. Part of the appeal comes from energy density. A little fusion fuel can release a very large amount of energy compared with chemical fuels. This is because fusion reaches into the nucleus, where energy is stored far more densely than in chemical bonds. When you burn coal or gas, you are rearranging electrons around atoms. When fusion happens, you are rearranging the nuclei themselves. It is like the difference between moving furniture around a room and rebuilding the foundations of the house. Both involve change, but one reaches much deeper. That deeper source is why stars can shine for so long. The sun does not burn like a log in a fireplace. It fuses hydrogen in its core slowly and steadily, turning light nuclei into heavier ones and releasing energy. It has been doing this for billions of years, and it will keep doing it for billions more. When people say fusion is the power of the stars, that is not just a dramatic phrase. It is physically true. Every sunrise is a reminder that fusion works beautifully when nature is allowed to build the reactor, make it enormous, and hold it together with gravity. Unfortunately, nature did not make the sun with maintenance access, replacement panels, or a convenient socket for the electrical grid. So humans have to build a much smaller version, and that changes everything. A power plant on Earth cannot rely on the sun's method. It cannot use the gravity of a star to squeeze fuel in the core. Instead, it must heat the fuel until the particles are moving fast enough to overcome their mutual repulsion. Atomic nuclei are positively charged, and positive charges do not enjoy being pushed together. They repel each other, like two guests at a dinner table who have both decided the other one is sitting too close. To make them fuse, you need extreme conditions. You need temperature, density, and confinement working together long enough for enough reactions to happen. This is where plasma enters. At the temperatures required for fusion, ordinary atoms cannot remain ordinary atoms. Electrons are stripped away. The fuel becomes plasma, a charged, glowing, intensely hot mixture of nuclei and electrons. Plasma is sometimes called the fourth state of matter, though it is not rare in the universe. In fact, most visible matter in the universe is plasma. Stars are plasma. The solar wind is plasma. Lightning is plasma. The glowing gas inside certain lamps is plasma. It is our everyday world of solid tables, liquid water, and breathable air that is a little unusual by cosmic standards. Inside a fusion machine, plasma has to be treated with great care. Since it is charged, it can be shaped by magnetic fields. This is one of the great tricks of fusion research. Instead of putting the plasma directly inside a physical bottle, scientists try to hold it with magnetism. A physical bottle would simply fail. The plasma is too hot, so the bottle must be invisible. Magnetic fields wrap around the plasma, guiding charged particles along paths and keeping them away from the reactor walls as much as possible. In a tokamak, the plasma is often shaped like a ring, moving inside a donut-shaped chamber. In a stellarator, the magnetic fields are twisted in more complex ways, like a sculpture designed by someone who had a very serious conversation with mathematics. This is already remarkable. Humans are trying to hold matter hotter than the sun with carefully shaped magnetic fields. Not by magic, not by wishful thinking, but by engineering superconducting magnets, vacuum chambers, heating systems, diagnostics, control computers, and a great many people who probably drink a lot of coffee while thinking about turbulence. But why go through all this trouble? Why not just use solar panels, wind turbines, hydroelectric dams, geothermal systems, batteries, and improved grids? The answer is not that fusion would replace every other energy source. The energy future will likely be a mix because the world is too complicated for one single solution to do everything. Wind is excellent where winds are strong. Solar is excellent where sunlight is abundant. Hydropower is excellent where geography allows it. Batteries and storage systems can help balance supply and demand. But fusion, if it becomes practical, could offer something rare. A dense, steady, controllable source of energy that does not depend on weather, daylight, or the burning of carbon. That steadiness matters. Modern grids need reliability. People want electricity at night, during storms, in winter, during heat waves, and on calm days when turbines are quiet. Energy storage can help, but long-duration storage at enormous scale remains a serious challenge. Fusion power plants could, in principle, provide continuous electricity, the kind that supports a grid when sunlight and wind fluctuate. They could be placed where power is needed, not only where coal or gas happen to be found. They might reduce dependence on fuel shipments crossing oceans and borders. In a world where energy security shapes politics, that is not a small thing. Another part of the promise is safety. Fusion reactions are difficult to start and difficult to maintain. That sounds like a disadvantage, and in the laboratory it certainly can feel like one, but for safety it has an upside. A fusion plasma is not like a pile of fuel that can burn out of control. The conditions needed for fusion are so delicate that if something goes wrong, the plasma cools and the reaction stops. It is a little like trying to keep a soap bubble floating in a hurricane. If the balance fails, the problem is usually not that it becomes unstoppable. The problem is that it stops immediately. For power production, this is frustrating. For runaway accident scenarios, it is reassuring. This does not mean fusion is free of hazards. A real fusion plant would still involve radiation, activated materials, high heat, powerful magnets, tritium handling, remote maintenance, and complex engineering systems. But the nature of the risk is different from many familiar nuclear fears. Fusion does not rely on a chain reaction in the same way fission does. The fuel inside the plasma at any moment is limited. If the plasma touches the wall too much, it loses heat and collapses. The machine must work very hard to keep fusion going. It is not eager to run away. It is eager, if anything, to quit. And that is why fusion researchers sometimes sound both hopeful and exhausted. The reaction is powerful, but the conditions are fragile. You're not simply lighting a match. You're creating a controlled state of matter that exists only because everything around it is arranged just so. The magnets, the vacuum, the heating, the fuel injection, the plasma shape, the exhaust, the wall conditions, the cooling systems, and the control software all have to cooperate. It is less like starting a fire and more like balancing a cathedral on a pin while asking it to boil water. Still, the reward is enormous. If fusion works at power plant scale, it could reshape how we think about energy abundance. Imagine a world where electricity is clean enough and plentiful enough that desalinating seawater becomes easier, producing green fuels becomes more practical, heavy industry can run without fossil carbon, and growing cities do not have to choose between development and pollution. That is the dream, at least. Fusion is not just about making cheaper electricity. It is about removing some of the harsh trade-offs that have followed energy for centuries. More power has often meant more smoke, more mining, more geopolitical dependence, more environmental damage. Fusion suggests, very carefully, that perhaps more power does not always have to mean more harm. Of course, that word perhaps is doing a lot of work, because the promise of fusion is not the same as a working fusion economy. The history of fusion is full of optimism, delay, progress, setbacks, new machines, improved records, and the familiar joke that fusion is always a few decades away. That joke is a little unfair, but not completely unfair. Fusion research has made real progress. Plasmas have become hotter, more stable, and better understood. Machines have achieved remarkable performance. Experiments have produced fusion energy in ways that would have seemed extraordinary to earlier generations. But making a net energy experiment is not the same as building a power plant. And building a power plant is not the same as building thousands of them reliably, economically, and safely. That distinction matters. A laboratory can celebrate a brief pulse of fusion. A power plant must operate for years. A laboratory can replace components after an experiment. A power plant must keep downtime under control. A laboratory can prove that physics works. A power plant must prove that materials, maintenance, supply chains, regulation, fuel breeding, electricity conversion, and cost all work together. The plasma is difficult, yes, but the plasma is not alone. Fusion has to become an industry, not just a beautiful moment inside a chamber. This brings us toward the part of the story that is easy to overlook. The promise of fusion depends not only on achieving the reaction, but on managing everything the reaction produces. Fusion gives energy, but it gives that energy in demanding ways. In the common deuterium and tritium reaction, much of the released energy is carried by neutrons. Because neutrons have no electric charge, magnetic fields do not hold them. They fly out of the plasma and strike the surrounding structure. That is not an accident. It is part of how the plant would capture energy. The neutrons heat the material around the plasma, and that heat can eventually be converted into electricity. But those same neutrons damage the material they strike. They knock atoms out of place. They change the structure of metals. They can make materials brittle. They can generate gases inside solids. They can activate components, making them radioactive for a time. So the very energy you want to capture arrives as a stream of microscopic wrecking balls. This is one of fusion's central ironies. The reaction is clean in the sense that it does not release carbon dioxide as combustion does, but the inside of the reactor is not a peaceful place. It is an extremely harsh environment, and everything near the plasma must be designed for punishment. Heat is another challenge. A future fusion plant must handle power flowing from the plasma to the surrounding surfaces. Some parts of the reactor, especially the exhaust region, may experience extreme heat loads. If the plasma becomes unstable, heat can arrive suddenly in bursts. A material might survive the average conditions but fail during repeated spikes. This is like saying a roof can handle normal rain but not hail, lightning, and someone occasionally throwing bricks from a helicopter. The average weather is not the whole story. Then there is the fuel cycle. Tritium is not abundant in nature. A working fusion plant using deuterium and tritium must breed new tritium by using fusion neutrons to interact with lithium in the blanket around the plasma. That means the reactor is not simply a device that consumes fuel. It must manufacture one of its fuels as it runs. The surrounding material must capture energy, protect the machine, and produce tritium efficiently enough to keep the plant going. If it does not, the elegant promise becomes a fuel supply problem with very expensive magnets. So when we say fusion promises almost impossible energy, we mean both halves of the phrase. The energy is almost impossible in how generous it seems. Dense, powerful, low carbon, fueled partly by material that can be drawn from water, capable of steady operation and linked to the same process that powers the stars. But it is also almost impossible in how hard it is to capture. The plasma must be hotter than anything we normally imagine. The confinement must be precise. The materials must survive radiation and heat. The fuel must be bred. The reactor must be maintained. The economics must make sense. The public must trust it. The whole system must become less like an experiment and more like a reliable power station humming somewhere beyond a city, quietly feeding the grid. There is something almost charming about the stubbornness of it. Humanity looked at the sun and said, yes, that, but smaller, indoors, connected to a turbine, with safety paperwork. And the universe, in its usual way, did not say no. It simply handed us a long list of conditions. That list is what makes fusion such a rich story. It is not a single miracle waiting to happen. It is a chain of problems, each one linked to the next. Solve the plasma heating, and you still need confinement. Improve confinement, and you still need exhaust control. Choose a wall material, and you still need it to survive neutrons. Add lithium for tritium breeding, and you still need chemical compatibility and heat removal. Make a powerful pulse, and you still need steady operation. Every success reveals the next challenge hiding behind it, like a set of doors in a very patient castle. But that is also how many great technologies arrive. Flight did not become practical the moment someone understood wings. It required engines, materials, control surfaces, fuel systems, navigation, maintenance, training, and airports full of people trying to keep luggage from going to the wrong city. Spaceflight did not happen because rockets alone existed. It needed guidance systems, heat shields, life support, launch infrastructure, and a frightening tolerance for vibration. Fusion will be no different. The star in the bottle is only the center of the machine. Around it must be an entire world of supporting systems, each one built to handle conditions that ordinary power plants never face. This is why the inner wall deserves our attention. It is where the promise of fusion meets the reality of matter. Grand ideas eventually have to touch a surface. Energy must become heat somewhere. Neutrons must land somewhere. Escaping particles must be absorbed somewhere. The plasma may be held by magnets, but the machine itself is still made of atoms, and atoms can only endure so much before they change. The wall is where the dream becomes physical. It is the place where the star says, "Here I am," and the reactor must answer, "Yes, but gently." So before we reach that wall, we first need to move closer to the thing it is meant to face. We need to understand the plasma itself, why it must become so hot, why it behaves so differently from an ordinary gas, and why even the smallest loss of control can turn a carefully shaped fusion experiment into a cooling, flickering reminder that stars are easy for the universe, but very difficult for us. To understand the wall of a fusion reactor, we have to first meet the thing it is trying not to touch, the plasma, that glowing, restless, electrically charged state of matter that sits at the heart of the machine like a tiny storm with stellar ambitions. It is tempting to picture it as a ball of fire, because fire is the hottest thing most of us know from ordinary life. But fusion plasma is not really fire. It is not wood burning in a fireplace, or gas burning under a kettle, or the blue flame of a stove quietly doing its job. Fire is chemistry. Fusion plasma is nuclear possibility. Fire rearranges electrons. Fusion asks atomic nuclei to come close enough to become something new, and that means the plasma has to be hot. Not just hot in the way a desert road is hot, not hot in the way molten lava is hot, not even hot in the way the surface of the sun is hot. Fusion plasma in a reactor can be hotter than the center of the sun, which sounds at first like a sentence that should not be allowed indoors. The center of the sun is already almost beyond imagination. Deep inside it, gravity presses matter together with crushing force. Hydrogen nuclei move through an ocean of plasma, colliding, scattering, and sometimes fusing through a slow chain of reactions. The sun does not need to rush. It has enormous mass. It has immense pressure. It has millions of kilometers of material wrapped around the core. It can afford to be patient. Fusion inside the sun is actually slow on the scale of individual particles, but the sun is so huge that slow reactions across such a vast amount of matter still produce the steady flood of energy that lights the solar system. A reactor on Earth has no such luxury. It cannot use the gravity of a star. It cannot squeeze fuel with the weight of a solar ocean above it. The plasma inside a machine is tiny compared with the sun, thinner, lighter, and far less compressed. So scientists compensate by raising the temperature. If the particles cannot be pushed together by star-sized pressure, they must be made to move faster. They must rush around with such tremendous energy that now and then, two nuclei come close enough for the fusion reaction to happen. This is why people say fusion plasma can be hotter than the sun. It is not because our machines are more powerful than stars in any simple way. It is because our machines are much smaller and much less dense, so they must use temperature where the sun uses gravity. It is like trying to recreate the pressure of an ocean using only a cup of water and a very determined kettle. Nature has one set of tools, humans have another. The star uses size, the reactor uses precision, heating, magnetism, and a truly unreasonable amount of patience. Now, when we say the plasma is hotter than the sun, it can sound terrifying. You might imagine the reactor glowing like a furnace that would melt everything for miles around. But temperature in a plasma is not quite the same as the everyday sensation of heat. Temperature is related to the motion of particles. In a fusion plasma, the particles are moving extremely fast, but the plasma is also very thin. There are far fewer particles in a given space than in a solid or liquid, so a very hot plasma can contain less total heat than a much cooler but denser material. This is one of those cases where physics gently reminds us that common sense is useful, but not always in charge. A spark from a firework can have a very high temperature, but because it is tiny, it may not contain enough heat to burn through everything it touches. A bathtub of warm water contains far more total heat than a glowing spark, even though the spark is hotter. In a similar way, fusion plasma can have an extraordinary temperature while still being something that must be carefully understood in terms of density, energy, and confinement. It is not a simple blob of heat. It is a special condition of matter, and that condition is delicate. Plasma begins when atoms are heated so much that electrons no longer stay attached to their nuclei. The atoms become ionized. Instead of neutral atoms drifting around, you get a mixture of free electrons and positively charged nuclei. Because the particles are charged, they respond to electric and magnetic fields. That one fact makes magnetic fusion possible. If plasma were neutral like ordinary gas, it would be much harder to hold without touching a container. But charged particles can be guided. They spiral around magnetic field lines. They can be shaped, squeezed, steered, and sometimes coaxed into behaving like a ring of artificial star matter. Sometimes people describe magnetic confinement as a bottle, but this bottle is not made of glass or steel. It is made of fields, invisible, carefully shaped, immensely powerful fields that try to keep the plasma floating away from the walls. In a tokamak, the plasma is arranged as a ring inside a donut-shaped chamber, circling around and around while magnets guide its motion. In a stellarator, the magnetic cage is twisted into a more complex shape, designed to keep the plasma stable without relying on quite the same internal current. Each design is a different attempt at the same strange task. Hold a thing too hot to touch by never touching it at all. That sounds almost elegant. And in some ways it is. But plasma does not behave like a well-trained candle flame. It has moods, it has waves, it has instabilities, it can ripple, drift, leak heat, form turbulent edges, and occasionally do something that makes scientists stare at their instruments with the quiet expression of people who know the machine has just become educational again. One of the hardest parts of fusion is that plasma is both a fuel and a moving system. It is not enough to heat it and leave it alone. It has to be kept stable long enough for many fusion reactions to happen. Heat must remain inside, fuel must be added, ash from the reaction must be removed, the shape must be controlled, the edge must be managed. The plasma must not lose too much energy to the surrounding material. It is a little like trying to keep a very energetic crowd dancing in a perfect circle, while the floor is shaking and the walls are allergic to dancers. To get the plasma hot enough, fusion machines use several heating methods. At first, electric current can heat the plasma, somewhat like current heating a wire, though the details are far more complicated. Then beams of fast neutral particles can be fired into the plasma, where they collide with the charged particles and transfer energy. Radio waves can also be used, tuned to interact with the plasma in specific ways, adding energy like a singer finding the resonant note of a glass. Each method is a way of feeding the plasma without simply throwing ordinary fire at it. The goal is not to make flames. The goal is to make nuclei move fast enough to fuse. And then, if the machine reaches the right conditions, the fusion reaction begins to help heat itself. In the most discussed fuel mixture, deuterium and tritium fuse and produce a helium nucleus and a neutron. The helium nucleus is charged, so magnetic fields can keep it inside the plasma for a while. As it moves through the plasma, it gives up energy through collisions, helping maintain the temperature. This is sometimes called self-heating, and it is one of the great milestones fusion researchers seek. A plasma that helps heat itself is a little closer to behaving like a star, though still with many engineers standing nearby, very much involved. The neutron, however, escapes. It does not feel the magnetic cage. It flies outward, carrying much of the energy from the reaction. This is useful for power generation, because the surrounding blanket can capture that neutron energy as heat. But for the plasma itself, the neutron is also a reminder that fusion energy does not stay neatly where you put it. Some of it leaves immediately, heading toward the wall and the materials beyond. So even in this section, while we are focused on the plasma, the wall is already waiting in the background. The plasma must be hot, but it must also be pure enough. This is one of the quieter and more unforgiving details. If atoms from the wall enter the plasma, they can cool it. Heavy atoms such as tungsten are especially troublesome if too much gets inside. They radiate energy strongly. In ordinary language, they help the plasma lose heat. A tiny amount of wall material can act like a chill spreading through the artificial star. That means the plasma and the wall have a complicated relationship. The plasma must be kept away from the wall because it can damage the wall. The wall must be kept out of the plasma because it can damage the plasma. Each one is dangerous to the other in its own way, which is not the ideal foundation for a peaceful household. This is why the edge of the plasma matters so much. The center may be the hottest region, where fusion conditions are strongest, but the edge is where the plasma speaks to the machine. Particles and energy move outward. Some are directed towards special exhaust areas, often called diverters. These regions are designed to handle particles leaving the plasma, remove helium ash, and protect the main wall as much as possible. The diverter is one of the hardest working parts of the reactor. It is not glamorous in the popular imagination, but it faces intense heat and particle flows. If the core of the plasma is the tiny star, the diverter is something like the star's drain, chimney and doormat, all asked to be heroic at once. At the plasma edge, sudden events can occur. In some machines, the plasma can release bursts of energy toward the wall. These bursts are not welcome. They can strike surfaces with damaging heat loads. Researchers work on ways to control, reduce, or spread out these events, because a power plant cannot afford to have its inner surfaces repeatedly shocked by bursts of escaping plasma energy. A laboratory experiment can learn from such behaviour. A commercial power plant would prefer the machine not throw tiny tantrums against its own lining. The plasma also has turbulence, not just turbulence like air shaking an airplane, but plasma turbulence, filled with charged particles, waves, and transport of heat. Turbulence can carry energy from the core toward the edge faster than desired. Fusion wants the heat to stay in the center. The plasma, being plasma, does not always agree. So researchers study confinement, trying to understand how energy leaks out and how magnetic shapes can reduce those losses. Every improvement in confinement means the plasma stays hot more easily. Every loss means the heating systems must work harder, and the wall may receive more punishment. There is an almost strange intimacy in this. The plasma is not solid, yet it has structure. It is not alive, yet it has behavior. It is not weather exactly, yet it has storms. It is not a creature, but it must be fed, heated, stabilized, and cleaned. It must be observed constantly with diagnostic instruments, because no one can simply look inside with ordinary eyes and understand what is happening. Scientists measure light, particles, magnetic fields, temperatures, densities, impurities, fluctuations, and currents. A fusion plasma is less like a campfire and more like an orchestra playing inside a thundercloud while surrounded by extremely expensive magnets. The comparison with the sun can be helpful, but only if we remember where it stops. The sun is not contained by walls, it is held together by gravity. If plasma in the sun moves around violently, the sun does not have an inner panel that needs replacing. If particles stream outward, they move into other layers of solar material. The sun can be messy because it is huge. It can absorb its own chaos. A fusion reactor cannot. It has edges, it has components, it has limits, it has maintenance schedules, it has to fit inside a building and eventually produce electricity at a price people can live with. So the plasma in a reactor is a kind of compromise between stellar physics and human engineering. It must be hot enough to fuse, but not so uncontrolled that it destroys the machine. It must be dense enough and confined long enough to produce useful reactions, but not allowed to touch the surrounding material in a destructive way. It must burn in a sense, though not as chemical fire burns. It must sustain itself enough to be practical, but remain controllable enough to be safe. The whole challenge is to create something close to a star while making sure it behaves more politely than a star ever had to. The vacuum around the plasma is also important. The reactor chamber must be emptied of ordinary air because air would cool and contaminate the plasma. Plasma does not like a room full of stray molecules. It needs carefully controlled conditions, with the right fuel particles injected at the right time. The chamber becomes a kind of artificial emptiness, a prepared space where the plasma can exist without immediately losing its energy to everything around it. Before the star can be born, the room must be made almost empty. There is something quietly beautiful about that. To create the brightest state of matter humans can control, first you remove nearly everything else. Then comes fuel injection. Deuterium and tritium must enter the plasma, sometimes as gas, sometimes as frozen pellets shot into the hot core. These pellets are tiny, but their journey is dramatic. They enter an environment so hot that they evaporate and ionize, becoming part of the plasma. Fueling a fusion reactor is not like tossing logs into a fireplace. It is more like feeding snowflakes into lightning and expecting the lightning to become a power plant. The plasma also produces helium ash. After fusion occurs, helium nuclei remain. Some of that helium helps heat the plasma for a while, but eventually it must be removed. If too much helium ash builds up, it dilutes the fuel and interferes with the reaction. So the reactor must breathe in a sense. It must receive fresh fuel and remove the products of fusion. It must keep the right mixture in the right state. A star can hold vast layers of material for billions of years. A reactor must manage a much smaller and more controlled cycle continuously. This is why fusion is not simply about reaching a high temperature. Reaching the temperature is impressive, but maintaining the right conditions is the deeper challenge. You can briefly make extremely hot plasma in many ways. Lightning does it. Certain laboratory devices do it. The real question is whether you can make a plasma that stays hot, stays confined, produces useful energy, protects the machine, and can operate again and again. A firework is bright, but it is not a furnace. A spark is hot, but it is not a power station. Fusion needs not only brilliance, but discipline. There is also the question of scale. A small plasma experiment can teach physics, but a power-producing reactor must be large and robust enough to produce more energy than it consumes, then capture that energy and turn it into electricity. The plasma must occupy a useful volume. The magnets must be strong and efficient. The heating systems must help start the process without consuming too much power overall. The wall and blanket must collect energy. The cooling system must carry heat away. The machine must be maintainable. The plasma is the heart, but the heart cannot live without the body. Still, it is the plasma that gives fusion its magic. It is the place where the ordinary rules of the room seem to change. Matter becomes charged and luminous. Magnetic fields become walls. Temperature becomes a measure of particles moving with incredible speed. Hydrogen, the simplest element, becomes the doorway to enormous energy. And all of it happens inside a machine whose purpose is not to explode, not to shine uselessly, but to produce steady heat that might someday turn turbines and feed homes. It is worth pausing on that thought. The future of fusion, if it arrives, may look surprisingly ordinary from the outside. A building, power lines, cooling systems, operators, maintenance crews, perhaps even a visitor centre with displays that try to explain plasma without making anyone too nervous. But inside, hidden behind shielding and steel, there would be a state of matter hotter than the sun's core, held away from the walls by magnetic fields, fed by isotopes of hydrogen, and watched by instruments faster and more patient than human senses. The extraordinary would be doing the ordinary job of making electricity. That is often how technology becomes part of life. What begins as impossible becomes impressive. What is impressive becomes industrial. What is industrial becomes background. The first electric lights were wonders. Now we notice them mostly when they fail. If fusion ever becomes common, people may one day live near fusion power plants without thinking much about the plasma inside. They may charge their devices, heat their homes, and ride trains powered partly by a tiny artificial star they never see. And somewhere inside that plant, the plasma would still be doing its delicate dance, too hot to touch, too useful to ignore, and too difficult to treat casually. But for all its beauty, the plasma cannot be separated from the thing around it. The hotter it becomes, the more important confinement becomes. The more reactions it produces, the more neutrons strike outward. The more energy it generates, the more heat must be handled at the edge. The plasma is the source of the promise, but also the source of the punishment. It gives fusion its power and creates the conditions that threaten the reactor itself. So when we picture the plasma hotter than the sun, we should not imagine only a glowing triumph at the centre of a machine. We should imagine a negotiation taking place every instant. The magnets say, "Stay here." The plasma says, "I am moving." The heating systems say, "Remain hot." The turbulence says, "I will carry heat outward." The fuel enters, the ash leaves, the neutrons escape, the wall waits, and the whole reactor depends on whether that negotiation can continue steadily enough to be useful. The plasma is not the final barrier. It is the reason the barrier must exist. It is the star matter that makes the dream worth chasing and the danger worth respecting. It must be created, held, heated, purified, shaped, and calmed. And even when everything goes well, even when the plasma stays suspended in its invisible cage, energy still escapes. Particles still reach the edge. Neutrons still fly outward. Heat still has to land somewhere. The artificial star may float, but its consequences cannot float forever, and that brings us closer to the first solid surface waiting beyond the magnetic field, the inner wall that must face what the plasma sends its way. The first wall of a fusion reactor is one of those parts of science that sounds simple only until you think about what it is being asked to do. A wall is usually something ordinary. It keeps the weather outside, It holds up a roof. It gives a room its shape. A wall is the reason you can sit calmly indoors while rain taps the window or wind pushes against the house. But in a fusion reactor, the word wall becomes almost unfair. This is not a brick wall, or a steel wall, or a polite boundary between one room and another. It is the first solid surface facing a machine made to hold plasma hotter than the centre of the sun. That is a very strange job for ordinary matter. The plasma itself is meant to float inside magnetic fields. In an ideal world, it would never touch anything. It would stay suspended in its invisible cage, flowing around the chamber, hot enough for fusion, stable enough to be useful, and distant enough from every surface that the reactor could simply collect energy and smile politely. But no real plasma is so perfectly behaved. Heat leaks out. Particles drift outward. Waves and turbulence carry energy toward the edge. Neutrons fly straight through the magnetic field as though the field is not even there. The plasma may be kept away from the wall in the main sense, but the wall still lives very close to the consequences of the plasma. So the first wall is not there because scientists expect the plasma to rest against it like soup in a bowl. It is there because a reactor has to be a physical machine, and every physical machine needs boundaries. Something has to define the chamber. Something has to support the systems around the plasma. Something has to catch the particles and radiation that escape. Something has to protect the magnets, pipes, sensors, and structures behind it. The first wall is the beginning of that protection. It is the first line of matter between a controlled artificial star and the rest of the machine. There is a quiet tension in this. The plasma must be close enough to the wall for the reactor to remain compact and practical, but not so close that it destroys the surface. The wall must be close enough to catch energy and shield the machine, but not so close in behavior that it contaminates the plasma. If tiny bits of wall material enter the plasma can cool. If too much heat from the plasma reaches the wall can erode, crack, melt, or change. The two are connected, but they must not become too intimate. A fusion reactor is, in a sense, an attempt to keep the most intense state of matter in the building from having a bad conversation with the building itself. This wall also has to work in a vacuum. The plasma chamber is not filled with ordinary air. Air would cool and contaminate the plasma almost immediately. So the first wall exists inside a carefully prepared emptiness, where stray gas has been removed, where fuel is introduced deliberately, where every impurity matters. That makes the wall more than a passive surface. It becomes part of the plasma environment. Its atoms, its coatings, its temperature, its roughness, its tiny defects, and its history of exposure can all influence what happens at the plasma edge. In everyday life, we rarely worry about the microscopic personality of a wall. A wall is a wall. If it does not fall over, we call it successful. In fusion, the wall must be judged atom by atom. What happens when a hydrogen isotope hits it? What happens when helium buries itself inside? What happens when a neutron knocks an atom from its place? What happens when heat arrives suddenly instead of gently? What happens after thousands of heating and cooling cycles? What happens when the wall is not new anymore, but tired, irradiated, roughened and changed by years of service? Fusion does not ask whether a material is strong in a simple way. It asks whether the material can remain useful while being slowly rearranged by a storm it cannot avoid. The first wall must face several kinds of attack at once. The most obvious is heat. Even if magnetic confinement works well, energy still reaches the wall. Some of it comes as radiation from the plasma. Some comes from particles that leave the confined region. Some arrives during brief events when plasma behavior changes quickly. A surface might endure steady heat, but sudden heat pulses can be much harder. If heat lands too strongly in one place, the surface can blister, crack, or melt. If it happens again and again, small damage becomes serious damage. A reactor cannot be built on the hope that the plasma will always be polite. Then there are the particles. At the edge of the plasma, charged particles can strike material surfaces, especially in regions designed to exhaust the plasma. When they hit, they can knock atoms out of the wall. This process is called sputtering. It is not dramatic like a hammer blow. It is more like a microscopic sandstorm, except the sand is made of energetic particles, and the surface is one of the most carefully chosen materials on Earth. Over time, sputtering can erode a surface. It can also send wall atoms back into the plasma, and if those atoms are heavy, they can radiate energy away and cool the plasma. So erosion is not only a materials problem, it is also a plasma problem. The wall can hurt the plasma by giving up tiny pieces of itself. There is also implantation. Particles from the plasma can enter the wall and become trapped. Hydrogen isotopes can bury themselves in the material. Helium can form bubbles. These trapped particles can change the wall from within. They may cause swelling, blistering, or changes in strength. In a reactor using tritium, this becomes especially important because tritium is radioactive and valuable. You do not want too much of it trapped in the wall. You want to know where it is, how much is retained, how to remove it, and how to keep the fuel cycle under control. A wall that quietly absorbs fuel is not just inconvenient. It complicates safety, operation, and accounting. And then come the neutrons. Neutrons are perhaps the most important reason fusion materials are so difficult. Magnetic fields can guide charged particles, but neutrons are neutral. They fly outward from the fusion reaction and pass through the plasma edge into the surrounding structures. When a fast neutron collides with atoms in the wall, it can knock them from their positions, creating damage inside the material. A solid metal looks stable to us because its atoms are arranged in a structure. Neutrons disturb that structure. They create vacancies where atoms used to be, interstitial atoms where atoms are shoved into awkward places, and small clusters of damage that can change how the material behaves. This is one of the cruel tricks of fusion engineering. The wall may look intact from the outside while its interior is slowly becoming a different kind of material. It can harden, it can become brittle, it can lose ductility, meaning it may crack instead of bending, it can swell. It can accumulate helium produced by nuclear reactions within the material. A surface that was designed as strong and reliable can become less forgiving over time. The damage is not only on the surface, it is deep in the atomic arrangement, where ordinary inspection is not as simple as looking for a dent. A future fusion power plant would have to deal with this continuously. It cannot replace the first wall after every short experiment. It cannot treat damage as a laboratory curiosity. It must plan for maintenance, replacement, remote handling, waste management, and downtime. The wall is not only a scientific question, it is an economic one. If components have to be replaced too often, the power plant becomes expensive and unreliable. If they are difficult to handle because they are activated by neutrons, maintenance becomes slower and more complex. If the wall fails unexpectedly, the reactor must shut down. So the first wall is not merely a protective layer. It is one of the deciding factors in whether fusion can become a real source of electricity. There is another challenge that feels almost contradictory. The first wall must protect what lies behind it, but in many designs the material behind it also has to help make fuel. In the common deuterium and tritium fusion reaction, tritium is consumed, and because natural tritium supplies are very limited, a power plant must breed more tritium using lithium. Neutrons from the plasma must enter the surrounding blanket, where they can interact with lithium and create new tritium. That means the region around the plasma cannot simply block everything. It must let the right particles go to the right places while still protecting the machine. It must capture energy as heat. It must help produce fuel. It must shield sensitive components. It must survive radiation. It must do several jobs that do not always like each other. This is why the phrase first wall can be misleading. It sounds like a single sheet of material, but in a real reactor it is part of a larger system. Behind it may be cooling channels, structural supports, breeding materials, neutron multipliers, shields, sensors, and complex assemblies called blankets. In some designs, the first wall and blanket are built together as replaceable modules. These modules must be installed, cooled, monitored, removed, and eventually replaced by machines, because the inside of a reactor after operation is not a place where a human technician can simply walk in with a toolbox and a cheerful attitude. Remote maintenance becomes part of the wall story. If the first wall is damaged or worn, how do you replace it? How do you reach it? How do you disconnect pipes or cooling systems? How do you handle components that may be hot, radioactive, or contaminated with tritium? How do you inspect surfaces hidden inside a complex machine? The answer involves robotics, precise engineering, modular design, and a great deal of planning before the reactor ever turns on. A fusion plant must be designed not only to work, but to be taken apart in the places where working will eventually damage it. The first wall also has to be cooled. Heat captured from the plasma and neutrons must go somewhere. In a power plant, that heat is not waste. It is the product. It must be carried away by a coolant and used to make electricity. But cooling the wall is tricky. The coolant must remove heat efficiently without weakening the structure, reacting dangerously with materials, or creating too many engineering problems of its own. Water is familiar and effective, but in certain neutron environments it can create complications. Helium gas is chemically gentle but harder to use for heat transfer. Liquid metals can carry heat well, but may be reactive, corrosive, or affected by magnetic fields. Every coolant is a choice with consequences. So now the wall is being asked to do even more. Face plasma, survive particles, endure neutrons, avoid contaminating the plasma, hold on to as little tritium as practical, transfer heat into coolant, stay strong under radiation, work with a breathing blanket, allow replacement by remote machines, and do all this while living in a powerful magnetic environment, inside a vacuum, near a plasma that would rather not behave like a quiet lamp. It is almost funny, in a very engineering sort of way. The plasma gets the dramatic reputation because it is hotter than the sun. The magnets get admiration because they are huge and powerful. The promise of fusion gets headlines because it sounds like a doorway to a cleaner future. Meanwhile, the first wall stands there like the sensible person at a party, quietly making sure the furniture does not catch fire. Except the furniture is a reactor, the party is a plasma, and the fire is nuclear fusion. One of the hard questions is what material the wall should be made of. There is no perfect material. If there were, fusion engineers would be much better rested. The ideal wall material would have a very high melting point, low erosion, low fuel retention, good thermal conductivity, resistance to neutron damage, low activation, compatibility with coolants, ease of manufacturing, reasonable cost, and no habit of poisoning the plasma. That is a long wish list. Materials are usually good at some things and bad at others. Tungsten can handle high temperatures and has low sputtering in many conditions, but it is heavy and can be dangerous to the plasma if too much enters it. Beryllium can help with oxygen impurities and has been used in plasma-facing components, but it is toxic and has its own lifetime issues. Carbon-based materials can tolerate heat shocks well, but they can trap too much tritium. Liquid metals may renew themselves, but they bring movement, chemistry, and control problems. The search for the wall is therefore not a search for perfection. It is a search for the best compromise inside a very narrow corridor of possibility. A material that survives heat might fail under neutron damage. A material that is kind to the plasma might retain fuel. A material that is easy to manufacture might not last long enough. A wall that performs well in a short experiment might be inadequate for years of power plant operation. Fusion materials are not judged by one heroic property. They are judged by whether all their weaknesses are manageable at the same time. Another complication is that the wall changes during operation. A clean, polished, carefully prepared surface at the start may not remain that way. Plasma exposure can roughen it. Neutrons can damage it. Deposits can form in some places as eroded material travels and settles elsewhere. Coatings can wear away. Cracks can appear. The surface becomes a record of its own history. In some machines, wall conditioning is used to improve plasma performance. Gases or coatings may be applied to reduce impurities and make the plasma edge behave better. This means the wall is not just installed and forgotten. It is prepared, monitored, and sometimes refreshed, like a stage that must be reset before the next performance, except the performance involves plasma physics, and the stage is being slowly sandblasted by ions. There is also a difference between the first wall and the diverter, though both face the plasma environment. The diverter is the region designed to receive much of the plasma exhaust. It handles particles and heat, leaving the plasma in a more concentrated way. In many reactor designs, the diverter may face some of the most extreme surface conditions in the machine. If the first wall is the boundary of the room, the diverter is the place where the room tries to empty its ash and heat. It is a component of enormous importance, because a fusion reactor must remove helium ash and control exhaust without destroying the surfaces that do the removing. The wall and diverter together form the plasma-facing world. They are where the clean dream of fusion becomes dusty, hot, irradiated, and practical. They remind us that a power plant cannot be made only of theories. It has to be made of materials, and materials are honest. They do not care how beautiful the idea is. They either survive the conditions or they do not. This is why research facilities test materials under plasma exposure, heat loads, and neutron-like damage. Scientists examine how surfaces erode, how cracks form, how hydrogen isotopes are retained, how helium bubbles develop, how coatings behave, and how metals change after bombardment. They use small samples, test stands, high heat flux devices, ion beams, neutron sources, and computer simulations. Each test answers a piece of the question. Not the whole question, because the full fusion environment is difficult to reproduce outside an actual reactor, but enough to guide the next design. Fusion materials research is a patient field. It is not always as flashy as a plasma record, but it may be just as important. The first wall is also where public imagination and engineering reality meet. People hear fusion and think of unlimited energy, clean power, a star in a bottle. Those phrases are not wrong, but they are incomplete. The bottle matters. The bottle is not just a metaphor, it has surfaces, bolts, channels, tiles, joints, welds, sensors, and failure modes. The star is not useful unless the bottle survives, and the bottle is not useful unless it can be repaired, cooled, and connected to a system that turns its captured heat into electricity. There is a humbling lesson there. The future sometimes depends on the unglamorous parts, not only on the bright plasma, but on the dull surface nearby. Not only on the moment of fusion, but on the years of material endurance after that moment. Not only on how much energy can be released, but on whether the machine can keep receiving that energy without slowly eating itself. So when we imagine the first wall, we should not picture it as a simple shield. It is more like the skin of the reactor. Skin protects, senses, exchanges heat, and takes damage so deeper systems do not have to. But unlike living skin, it does not heal itself easily, at least not in most solid wall designs. It must be designed to tolerate injury, to be replaceable, and perhaps one day to include materials or liquid surfaces that can renew themselves in limited ways. The wall is the reactor's contact with the violence it is trying to use. It is where a human-built machine learns how close it can stand to a star, and this closeness is the heart of the problem. Fusion wants intimacy with extreme energy. It wants to create plasma fierce enough to release nuclear power, but controlled enough to sit inside a machine. It wants neutrons energetic enough to heat a blanket and breed fuel, but not so damaging that components fail too quickly. It wants walls close enough to make a compact reactor, but protected enough to last. Every design must choose where to place the burden. More shielding may protect magnets, but make the machine larger. Better cooling may require more complex channels. Stronger materials may create impurity concerns. Better plasma performance may increase surface loads. Nothing is free, not even the energy of the stars. The first wall stands at the center of those trade-offs. It is a boundary, a tool, a shield, a heat collector, and a witness. It sees the plasma not as a beautiful glow in a diagram, but as radiation, heat, particles, and damage. It receives what the magnetic cage cannot fully hold. It marks the place where the artificial star stops being an elegant idea and becomes a physical neighbour. And once we understand that, the next question becomes unavoidable. What exactly is this wall enduring every second the reactor operates? How does heat strike it? How do neutrons alter it? How does matter that seems solid become weakened by invisible impacts? Why can a surface survive one pulse, but not thousands? The first wall is the boundary, but the real story of its survival is written in the slow destruction of materials under conditions that almost nothing on Earth was naturally made to face. Matter feels dependable because our lives are built on its patience. A table stays a table, a spoon stays a spoon, a wall stays where the builder left it, unless someone is having a very dramatic renovation. In ordinary life, solid things give us the comforting impression that atoms are loyal. They hold their places. They form metal, stone, glass, ceramic, and concrete. They let us build bridges, kettles, cars, towers, engines, and quiet rooms where someone can listen to physics while trying not to think about tomorrow too much. But inside a fusion reactor, matter is asked to keep that loyalty under conditions that are deeply unfair. The first wall does not face one simple enemy. It faces heat from the plasma, particles from the plasma edge, radiation from the burning fuel, and neutrons that move through the machine like invisible hail. Each of these can harm a material in a different way. Heat tries to soften, crack, melt, and fatigue it. Charged particles try to erode the surface, knocking atoms away grain by grain. Helium and hydrogen try to hide inside the material, making bubbles, blisters, and weak spots. Neutrons go deeper, striking the atomic structure itself, rearranging what seemed solid from within. This is not destruction as a single dramatic moment. It is slow, repeated, microscopic damage. The kind that makes a material look calm from a distance while its inner order is being patiently disturbed. That slow destruction is one of the great problems at the heart of fusion energy. It is easy to say that a reactor wall must survive heat and radiation. It is much harder to design a material that actually does it for long periods, under real operating conditions, while being cooled, stressed, bombarded, activated, and occasionally surprised by the plasma. Fusion does not simply ask, can this material survive a hot moment? It asks, can this material survive millions upon millions of small insults and still remain useful? Let us begin with heat, because heat is the most familiar part of the problem. We know what heat does. It cooks food, melts ice, softens wax, warps plastic, and turns a forgotten pan into a smoky little moral lesson. In a fusion reactor, heat is both the purpose and the threat. The reactor is built to produce heat, because heat is how the released fusion energy can eventually become electricity. But the same heat that makes fusion valuable also attacks the surfaces that receive it. The plasma is supposed to remain mostly confined by magnetic fields, but energy still escapes. Some of it arrives as radiation. Some comes with particles reaching the edge. Some is directed towards special exhaust regions. Some may arrive in sudden bursts when the plasma becomes unstable. The average heat load matters, but the pattern matters too. A material might cope with steady heating if it is cooled properly, but repeated pulses can be much worse. Heat arrives quickly, the surface expands, then cools and contracts, again and again. Expansion and contraction may sound harmless, like a material quietly breathing. But if the breathing is forced, uneven, and repeated under extreme conditions, it can create stress. This is called thermal fatigue. You can imagine bending a paperclip back and forth. One bend is fine, a few bends are fine, but after enough repetitions the metal weakens and snaps. In a reactor wall, the bending is not always visible. The surface and deeper layers heat at different rates. One region expands while another resists. Tiny cracks can begin. At first, they are too small to matter. Then they grow. Then they link. Then a piece of material that once seemed reliable has become a risk. Heat can also change the surface itself. If the temperature rises too much, atoms can move more easily. The material can recrystallize, soften, or lose strength. If a surface melts, even briefly, the problem becomes more serious. Liquid metal can move, splash, roughen, or resolidify in damaged shapes. A wall that was carefully manufactured with smooth surfaces and controlled geometry can become uneven. Uneven surfaces can interact badly with plasma, creating new places where heat concentrates or material erodes. Damage changes the wall, and the changed wall can invite more damage. It is a very unhelpful friendship. The most intense heat loads are often associated with the divertor, the region that receives plasma exhaust. The divertor is designed to take punishment, but design does not make punishment gentle. It must handle particles and heat leaving the plasma, help remove helium ash, and protect the rest of the chamber. If the first wall is the reactor skin, the divertor is a place where the skin has agreed to stand under the waterfall. A waterfall made of heat, charged particles, and bad news for surface atoms. To survive, these surfaces need cooling. Cooling channels may carry water, helium, or other coolants behind the plasma-facing material. The heat must travel from the surface into the coolant, then onward to systems that can use it. But cooling is not a magic eraser. It creates its own stresses. A very hot front surface and a cooler back surface mean temperature differences inside the material. Temperature differences create expansion differences. Expansion differences create mechanical stress. The better you remove heat, the more carefully you must manage the structure that carries it away. It is a little like trying to cool a baking tray with ice water while it is still in the oven. Useful in principle, but the tray may have opinions. Then come the charged particles. At the edge of the plasma, ions can strike the wall or divertor surfaces. When they hit with enough energy, they can knock atoms out of the material. This is sputtering. It is not like slicing off a chip with a knife. It is more like a long, invisible drizzle of impacts, each one removing a few atoms here, a few atoms there. Over time, the surface erodes, the shape changes, the material becomes thinner. Atoms released from the wall may travel through the chamber and settle elsewhere, creating deposits. Some may enter the plasma and cool it. In a fusion reactor, even erosion has consequences beyond simple wear. If wall material enters the plasma, it becomes an impurity. Light impurities can be troublesome. Heavy impurities can be worse. Heavy atoms radiate energy efficiently, which means they can drain heat from the plasma. A plasma that loses too much heat cannot maintain fusion conditions. So a damaged wall does not merely lose material, it can poison the very star it is meant to contain. The wall must endure the plasma, but it must also avoid becoming part of it. Some materials resist sputtering better than others. Tungsten, for example, is valued partly because it is difficult to sputter in many relevant conditions and can survive very high temperatures. But even tungsten is not invincible. Under repeated exposure, it can roughen, crack, and change. If it does enter the plasma, its atoms can be especially cooling because tungsten is heavy. So the material that survives well as a wall can become dangerous if the wall gives up too much of it. Fusion has a way of making every answer conditional. Particles can also become trapped inside surfaces. Hydrogen isotopes from the fuel can enter the wall. Deuterium may be retained. Tritium may be retained. Helium can also become embedded. At first, this sounds like a small detail, a few particles hiding in a wall. But in a fusion reactor, fuel retention is a serious matter. Tritium is radioactive, limited, and must be carefully tracked. If too much tritium becomes trapped in plasma-facing materials or deposits, it complicates safety and fuel management. The reactor must know where its fuel is. A wall that quietly stores fuel without permission is like a pantry that eats your groceries and then refuses to explain itself. Helium creates another problem. Helium does not fit neatly inside metal structures. When helium atoms are produced or implanted in a material, they can gather into bubbles. These bubbles may form beneath the surface. Over time, they can grow, causing swelling, blistering, and weakening. In some conditions, the surface can develop fine tendrils or rough, fragile structures. A smooth metal can become fuzzy at microscopic scales, which sounds almost charming until you remember that this fuzz exists inside a machine that needs precise surfaces and reliable heat removal. Tiny surface changes can affect how particles strike, how heat spreads, and how erosion continues. Hydrogen can also affect metals in damaging ways. In some materials, hydrogen can contribute to embrittlement, making the material more likely to crack. It can move through the structure, collect at defects, and change how the metal responds to stress. Again, the damage is not always visible at first. The material may look strong until the wrong combination of load, temperature, and internal changes reveals that its toughness has quietly faded. And then there are neutrons, the deepest troublemakers in the fusion story. In the deuterium and tritium reaction most often discussed for early fusion power plants, the neutron carries away a large share of the released energy. Because it has no electric charge, it ignores the magnetic fields that confine the plasma. It travels outward and collides with the material surrounding the plasma. This is useful because the neutron energy can be captured as heat. It is also damaging because neutrons strike atoms inside the solid material, not just at the surface. A metal is not a continuous smooth substance at the atomic level. It is an arrangement of atoms in a pattern. That pattern gives the metal many of its properties. Strength, ductility, thermal conductivity, resistance to cracking. All of these depend on the arrangement of atoms, grains, defects, and phases inside the material. When energetic neutrons collide with atoms, they can knock them from their proper places. One displaced atom can hit others, producing a little cascade of damage. In the end, you may have vacancies, atoms squeezed into awkward positions, clusters of defects, and regions where the crystal structure has been disturbed. This kind of damage is strange because it happens inside the material, everywhere neutrons penetrate. A surface scratch is visible. Neutron damage is more like aging in the bones of the metal. The material may harden, but harder is not always better. A hardened material can become less ductile. It may resist deformation for a while, then crack suddenly. Ductility is the ability to bend or stretch without breaking, and in a complex machine, ductility is a kind of mercy. It lets a material absorb stress. If neutron damage removes that mercy, the material becomes brittle. Brittle materials are dangerous because they can fail without much warning. Neutrons can also cause transmutation. That means they can change one element into another through nuclear reactions. This can produce gases such as helium and hydrogen inside the material itself, not just implanted from the plasma surface, but born within the wall by neutron interactions. These gases can gather at defects, grain boundaries, and tiny cavities, encouraging swelling and embrittlement. The wall is not only being hit, it is being changed chemically and structurally by the radiation passing through it. Radiation can also make materials radioactive. When neutrons are captured by atomic nuclei in the wall or surrounding structures, they can create unstable isotopes. This is called activation. Fusion does not produce the same long-lived waste profile as traditional fission reactors, but activated components are still a real issue. The inner wall and blanket materials may become radioactive after operation and require remote handling, cooling time, storage, and disposal planning. The choice of material matters greatly. Engineers prefer materials that do not become dangerously radioactive for long periods. But again, the wish list is long and reality is stubborn. Activation also affects maintenance. After a fusion reactor has operated, the inside of the machine cannot simply be entered by workers in the ordinary way. Components near the plasma may be radioactive and contaminated with tritium. Maintenance must often be done remotely, using robotic systems that can remove and replace heavy, complex modules. That means material damage becomes a design problem for the entire reactor layout. If the wall is expected to degrade, it must be replaceable. If it is replaceable, the machine must include access routes, connectors, handling systems, and procedures. This slow destruction of matter shapes the architecture of the power plant. There is another subtle issue. Neutron damage can reduce thermal conductivity. Thermal conductivity is the ability of a material to carry heat. If the wall material becomes worse at conducting heat, then its surface may run hotter under the same conditions. Hotter surfaces may crack more easily, erode faster, or retain more fuel. So neutron damage can make heat damage worse. Heat damage can roughen surfaces and change plasma interactions. Plasma interactions can increase erosion and fuel retention. Everything connects, which is very satisfying in a textbook and very annoying in a reactor. Fusion materials also face mechanical loads. The wall and blanket structures are not floating peacefully in a philosophical vacuum. They are attached to supports, cooled by flowing fluids, surrounded by magnetic fields, and exposed to pressure differences. Powerful magnets create forces in nearby conducting materials. Coolants create internal pressures, temperature gradients create stress. Neutron damage changes mechanical properties. The result is a material that must be strong under ordinary engineering loads, while also being modified by radiation and heat. It is like asking a bridge to carry traffic while the steel inside it is being slowly rearranged by invisible billiard balls. Because of all this, fusion researchers study something called material lifetime. This is not just a question of when the wall melts. Melting would be obvious. Lifetime is about when the material no longer satisfies all the requirements at once. Perhaps it has eroded too much. Perhaps it has cracked. Perhaps it retains too much tritium. Perhaps it has become too brittle. Perhaps it conducts heat poorly. Perhaps it releases too many impurities into the plasma. Perhaps it has become difficult to maintain safely. Failure is not always a single event. Sometimes failure means the material is still there, but no longer trustworthy. Testing these materials is difficult because the true fusion environment is hard to reproduce. A real reactor exposes materials to high heat, plasma particles, neutrons, magnetic fields, mechanical stress, and long operating times all together. Laboratory tests can reproduce pieces of this environment. One device can test heat loads, another can expose samples to plasma. Ion beams can simulate some radiation damage. Neutron sources can study displacement damage. Computer models can predict how defects evolve. But the full combination is challenging. This means material development requires both experiments and careful imagination. Scientists must learn from partial tests and still design for a future environment more complex than any one test can fully capture. There is a gentle irony here. Fusion promises power from the simplest atoms, hydrogen isotopes, but to use that power we need some of the most sophisticated materials ever developed. The fuel may be simple, the wall is not. It must be made with carefully controlled composition, microstructure, manufacturing methods, cooling design, coatings, joints, and replacement plans. The smallest atoms demand the cleverest surfaces, and the destruction is not only physical, it is informational. Every time the wall changes, the reactor must understand what changed. Sensors and diagnostics become important. Surface temperature, erosion, impurity levels, tritium retention, radiation damage, coolant behavior, and plasma edge conditions all need monitoring. A future reactor will not simply trust its wall, it will watch it, quietly, constantly, perhaps with systems that detect early signs of trouble before damage becomes serious. The wall becomes not just a passive barrier, but part of a monitored living machine. When we speak of the slow destruction of matter, it can sound discouraging, and in a way, it is. Matter has limits. There is no material that laughs off every neutron, every heat pulse, every particle impact, and every chemical complication. But this is not the same as saying fusion is impossible. engineering has always lived inside limits. Jet engines operate with blades facing temperatures that would ruin ordinary metals, so engineers invented superalloys, coatings, cooling channels, and inspection methods. Spacecraft face vacuum, radiation, vibration, and re-entry heat. So engineers layered materials and designed systems around those extremes. Fusion will require the same kind of humility. Not a magical wall, but a wall designed with damage in mind. A successful fusion wall may not be permanent, it may be replaceable, it may be modular, it may be coated, it may be designed to erode slowly in acceptable ways, it may use materials that become less radioactive after reasonable periods. It may rely on clever cooling and plasma control to reduce the worst loads. It may combine solid surfaces with liquid metals in some places. It may use different materials in different regions, because the main wall and diverter do not face identical conditions. The solution may not be one heroic substance. It may be a carefully arranged system of compromises. Still, the basic truth remains. Fusion does not only ask whether we can make plasma hot enough, it asks whether we can build matter patient enough to live beside it. The heat tries to crack the surface, the particles try to erode it, the hydrogen tries to hide in it, the helium tries to bubble through it, the neutrons try to rearrange it. The reactor asks the wall to keep working anyway, not once, not briefly, but as part of a power plant that must make sense outside the laboratory. There is something almost moving about that. A fusion reactor is often described by its most spectacular feature, the plasma, the tiny sun, the star in a bottle. But the story of its success may depend on quieter forms of endurance. A surface that does not melt too soon. A metal that does not crack too easily. A coating that keeps impurities under control. A structure that can be removed and replaced by a robot after years of invisible damage. The future of almost impossible energy may depend on very practical questions about atoms staying where they belong, and once we see how harsh the environment really is, the search for wall materials begins to feel less like shopping for the strongest metal and more like choosing a companion for an impossible journey. Some candidates are strong against heat but troublesome in the plasma. Some are light and useful but dangerous to handle. Some protect the surface but wear away. Some might renew themselves by flowing like liquid, but bring their own strange engineering demands. The next step is to look at the materials that have tried, or may try, to stand between fusion fire and the world, beginning with some of the most important solid candidates in the long search for a wall that can survive. When engineers look for a material that can face the inside of a fusion reactor, they are not really looking for strength in the ordinary sense. They are not asking which metal would make a good bridge, or which alloy could hold up a tower, or which surface would survive a hot pan in a kitchen where someone has become distracted by a documentary. They are asking something much harsher. What material can stand near plasma hotter than the sun, endure extreme heat, resist being eroded atom by atom, avoid poisoning the plasma, survive neutron damage, release trapped fuel, carry heat away, and still be manufacturable in the real world? That is not a normal job interview for a piece of matter. If the first wall is the reactor skin, then its material is the skin's character. Some materials are stubborn against heat, some are chemically useful, some are light and friendly to the plasma, some are heavy and hard to knock apart, some can survive one kind of punishment, but fail under another. The difficulty is that fusion does not give a material only one exam. It gives the material several exams at the same time, in different languages, while the desk is on fire. Tungsten is one of the most famous candidates because it has a very simple virtue. It can tolerate extremely high temperatures. Among metals, it is one of the great survivors of heat. It has a very high melting point, much higher than familiar structural metals such as iron, copper, or aluminum. That makes tungsten attractive for the places in a fusion reactor that face intense heat loads, especially in regions where plasma exhaust is directed. If you need a metal that does not panic easily when things become hot, Tungsten walks into the room with a calm expression and a heavy suitcase. It is dense, hard, and difficult to melt. It also resists sputtering better than many lighter materials. Sputtering, as we have seen, is the process where incoming particles knock atoms out of a surface. In a fusion reactor, that matters because every atom removed from the wall is both a little bit of damage and a possible impurity that may enter the plasma. Tungsten atoms are not easily knocked away under many relevant conditions, so a tungsten surface can erode more slowly. That is a serious advantage. A wall that loses itself too quickly is not really a wall for long. It is more like a very expensive donation to the plasma. Tungsten also has good thermal conductivity, compared with many materials that might otherwise be considered for such harsh settings. Heat that lands on the surface must be moved away quickly into cooling systems. If heat lingers at the surface, temperatures rise, stresses grow, and damage becomes more likely. A plasma-facing material does not only need to avoid melting, it must help carry heat away fast enough that the whole component remains within manageable limits. Tungsten can help with that, especially when paired with carefully designed cooling structures behind it. So at first glance, tungsten sounds almost ideal. It is hot enough for the job, strong enough to be respected, and stubborn enough to survive particle bombardment better than many competitors. But fusion has a habit of taking promising answers and quietly attaching footnotes. The first problem is that tungsten is a heavy element. That matters because if tungsten atoms enter the plasma, they can radiate energy very efficiently. In simpler terms, tungsten impurities can cool the plasma, and for fusion, cooling the plasma is exactly what you do not want. The plasma must remain incredibly hot for the reaction to continue. Even small amounts of heavy impurity can drain energy from it, so tungsten is excellent as long as it stays where it belongs. If it leaves the wall and joins the plasma, it becomes a problem. This gives tungsten a strange double nature. It is attractive because it does not erode easily, but dangerous because the atoms that do erode can be very damaging to plasma performance. It is like hiring a very reliable guard who is wonderful at the door, but causes enormous confusion if he wanders into the dance floor. The solution is not simply to abandon tungsten, because its advantages are too important. The solution is to control plasma conditions, reduce erosion, manage edge behavior, and design surfaces so tungsten contamination stays low. Once again, the material answer depends on the plasma answer, and the plasma answer depends on the material answer. Fusion does enjoy making everyone work together. Neutron damage is another challenge. Tungsten may survive heat well, but fast neutrons can alter its structure. They can knock atoms out of place, create defects, and produce changes that make the material more brittle. Tungsten is already not famous for being soft and forgiving. Under irradiation, its tendency toward brittleness can become more serious. A material that is hard and strong may still crack if it cannot absorb stress. In the hot, stressed, irradiated environment of a fusion reactor, toughness matters. A material must not only resist damage, it must remain able to tolerate the damage it receives. Tungsten can also develop surface changes under helium exposure. Helium from the plasma or produced by nuclear reactions can gather in the material, forming bubbles and altering the surface. Under certain conditions, tungsten surfaces can become rough or develop fine structures. These changes may affect how the surface handles heat and how it interacts with the plasma. A smooth tungsten tile at the start of operation may not remain smooth forever. The surface becomes a history book written by impacts, heat, helium, and time. Unfortunately, the book is written in cracks, bubbles, and missing atoms, which is not the most relaxing literary genre. Another practical issue is joining tungsten to other materials. A plasma-facing surface may be tungsten, but behind it you need support structures and cooling channels, often made of different materials. Different materials expand differently when heated. They may respond differently to radiation. They may be difficult to bond together. A joint between tungsten and another metal must carry heat, survive stress, and remain intact after repeated thermal cycling. In a fusion reactor, a joint is not just a seam. It is a place where failure might begin. Every connection must be treated as a serious engineering challenge. Still, tungsten remains one of the leading materials because the conditions are so extreme that its strengths are hard to ignore. It is not perfect, but perfection is not on the shelf. Tungsten is the kind of material engineers choose when they know the environment will be brutal, and the alternatives may fail even faster. It is the heavy shield, the heat survivor, the stubborn surface that says, perhaps not forever, but maybe long enough if you treat me carefully. Beryllium tells a very different story. Where tungsten is heavy and severe, beryllium is light. It sits near the other end of the material personality chart, if such a chart existed, and was not immediately questioned by serious metallurgists. Beryllium has been used in fusion research partly because of how it interacts with plasma impurities. In machines where plasma purity matters deeply, the wall is not just a passive object. It can help shape the chemistry of the plasma edge. Beryllium can bind with oxygen and reduce certain impurities that would otherwise cool the plasma. In that sense, it can act a little like a cleaner, quietly absorbing troublesome guests before they disrupt the party. This is useful because oxygen is a strong radiator in plasma conditions. If too much oxygen enters the plasma, it can carry energy away and interfere with performance. Beryllium can help by capturing oxygen at the wall, reducing the impurity burden. That made it attractive in some experimental designs. It is also a low atomic number material, which means that if some beryllium enters the plasma, it is generally less damaging than heavy impurities such as tungsten. Light impurities still matter, but they do not radiate energy in the same devastating way as very heavy ones. So beryllium is more forgiving from the plasma's point of view. Beryllium also has nuclear properties that can be useful in blanket concepts, because it can help multiply neutrons in certain reactions. More neutrons can help with tritium breeding, which is important in a reactor that must make its own tritium fuel. This does not mean beryllium magically solves the breeding problem, but it can play a role in the broader design. In fusion, a material may be chosen not only for what it does at the surface, but for what it contributes to the entire system of heat capture, shielding, and fuel production. But beryllium has its own very serious problems. The first is toxicity. Beryllium dust is hazardous if inhaled. It can cause severe lung disease and requires careful handling. This matters greatly in a fusion plant, where plasma-facing components will eventually be removed, repaired, inspected, or disposed of. If those components contain beryllium, maintenance becomes more complicated. Safety procedures become stricter. Dust control becomes essential. A material might behave well in the plasma, but if it is dangerous for workers and difficult to manage during maintenance, that advantage comes with a cost. Beryllium also has a relatively low melting point compared with tungsten. It cannot endure the same extreme surface temperatures. That makes it less suitable for the most heat-intense regions. In a fusion reactor, different areas face different conditions. A main wall surface may face one kind of load, while a diverter target faces another, often much harsher. Beryllium may be useful in some places, but it is not the natural choice for the areas that must take the most concentrated heat. It can help with plasma chemistry, but it does not have tungsten's calm resistance to melting. It also erodes. Under plasma exposure, beryllium can be sputtered and transported around the chamber. It may redeposit in other places. Those deposits can trap hydrogen isotopes, including tritium. This is not a minor detail. Tritium retention is one of the major concerns for fusion operation. If eroded beryllium travels through the chamber and forms deposits in cooler or hidden regions, those deposits may hold fuel. Over time, the total inventory of trapped tritium can become a safety and regulatory concern. The reactor must track and control tritium, not let it quietly collect in dusty corners like a radioactive version of household lint. The combination of erosion, redeposition, toxicity, and fuel retention makes beryllium complicated. It offers plasma benefits, but at the price of handling and lifetime issues. Like tungsten, it solves some problems while creating others. That is a recurring pattern in fusion materials. Every candidate arrives with a resume and a small collection of secrets. There is also the question of neutron damage. Beryllium exposed to neutron radiation can change, swell, crack, and produce helium. Under irradiation, it can become more brittle. Because it may be used in regions near the plasma or in blanket structures, its behaviour under long-term neutron exposure is crucial. Materials do not get to choose which particles they meet. If they are placed near a fusion plasma, neutrons will arrive, whether the material is in the mood or not. The contrast between tungsten and beryllium is useful because it shows the central dilemma. Tungsten is excellent against heat and erosion, but dangerous as a heavy impurity and vulnerable to radiation-induced brittleness. Beryllium is gentler to the plasma and chemically useful, but toxic, more easily melted, and prone to erosion and tritium retention issues. One is the stern heat shield. The other is the lighter chemical helper. Neither is the perfect answer. Both belong to the conversation because fusion is not asking one simple question. In some reactor concepts, materials are layered or placed according to function. The hottest regions may use tungsten. Other surfaces may use lighter materials. Coatings may be applied. Wall conditioning may modify the surface before or during operation. Instead of one material doing everything, the machine may use a carefully arranged set of materials, each placed where its strengths matter most and its weaknesses can be managed. This is sensible, but it creates interfaces, joints, manufacturing challenges, and maintenance complexity. A reactor wall made of multiple materials may perform better, but it also becomes a more complicated object to build and repair. There is also a deeper question about how long any solid wall can last. Tungsten and beryllium are both solid materials. They have surfaces that erode, crack, and retain fuel. They have internal structures that neutron damage can alter. They can be replaced, but replacement means downtime, robotics, activated waste, and cost. If the wall has to face years of operation, perhaps the solution is not simply to find a better solid. Perhaps the solution is to change what we mean by wall. This is where ideas such as coatings and liquid metals begin to enter the story, but before moving there, it is worth staying with the solid wall problem a little longer. The dream of a solid wall is attractive because solids are familiar. They can be machined, tested, bolted, cooled, inspected, and modelled. Engineers understand how to build with solids. A tungsten diverter tile, for example, may be difficult, but it is still a solid component. It can be manufactured to a shape, attached to a heat sink, and installed as part of a module. It fits within the long tradition of engineering objects that must be strong, hot, and replaceable. But fusion pushes solid materials toward their limits. A solid wall has a fixed surface. Damage accumulates. If atoms are removed, the wall thins. If cracks form, they may grow. If helium bubbles appear, the surface changes. If neutron damage makes the material brittle, the structure becomes less reliable. A solid wall remembers every punishment. It carries scars. Sometimes those scars can be tolerated. Sometimes they cannot. The difficulty is designing a wall whose memory of damage does not become fatal too soon. One strategy is to reduce the punishment. Better plasma control can reduce heat pulses and particle loads. Better magnetic configurations can spread exhaust over a larger area. Advanced diverter designs can cool and disperse plasma before it reaches surfaces. Impurity seeding can deliberately add small amounts of selected atoms to the plasma edge, causing energy to radiate away in a controlled region before it strikes the wall. This sounds odd, because impurities are usually bad, but controlled impurity radiation can be useful if it spreads heat more gently. The trick is to cool the edge without cooling the core too much. Fusion often works like this. The solution is not simply less impurity or more impurity, but the right impurity in the right place at the right time, very relaxing if you happen to be a control system. Another strategy is to make materials stronger under radiation. Researchers study tungsten alloys, advanced steels, composites, ceramics, and engineered microstructures. Sometimes adding small amounts of other elements can improve toughness or radiation resistance. Sometimes controlling grain size can change how defects move and gather. Nanostructured materials may offer new pathways for absorbing damage, but every improvement must be tested against the whole fusion environment. An alloy that is tougher may have worse thermal conductivity. A material that handles neutrons well may be difficult to manufacture. A composite that works in small samples may be hard to build into large components. Materials science is a field of trade-offs wearing a lab coat. For beryllium, the future is especially uncertain in some designs because of its toxicity and lifetime issues. It has played an important role in understanding plasma wall interactions, and it may still appear in certain systems, but many researchers look for alternatives that avoid its handling problems. A material can be scientifically useful and still awkward as a long-term industrial choice. A power plant is not only an experiment, it is a workplace, a regulated facility, and a machine that must be maintained by real people using real procedures. Toxic dust does not become charming just because the plasma likes the wall chemistry. Tungsten, meanwhile, is likely to remain central in the conversation, especially for divertor surfaces. Its heat resistance is too valuable, but the challenge is making tungsten components that can survive not only heat, but cycling, neutron damage, and mechanical stress. Engineers must learn how tungsten behaves after irradiation, how it fails, how to join it to cooling structures, how to shape it to reduce stress, and how to prevent too much tungsten from entering the plasma. In a way, tungsten is not a complete answer. It is a foundation for many more questions. There is a quiet humility in this search. In popular imagination, advanced technology often looks sleek and decisive, a brilliant machine made of the perfect substance. But real fusion research is messier and more patient. It asks whether a roughened surface can still be acceptable, whether a crack can be tolerated until the next maintenance cycle, whether a coating can be renewed, whether erosion can be predicted, whether impurities can be controlled, whether a material can become slightly damaged without becoming useless. The future may not be built from flawless materials, but from materials whose flaws are understood well enough to manage. That understanding is what turns extreme physics into engineering. A star does not need a wall, a power plant does. A star does not care whether tungsten becomes brittle, a power plant does. A star does not worry about beryllium dust, tritium retention, remote replacement, or whether a coolant channel can be inspected after years of operation. A power plant is made of responsibilities. The wall material must satisfy physics, engineering, safety, maintenance, economics, and time. It must be good not only during the first bright experiment, but after the 1000th hot cycle, after the surface has changed, after the neutrons have done their quiet work. So tungsten and beryllium are not simply materials, they are lessons. Tungsten teaches that surviving heat is not enough if the plasma cannot tolerate contamination, and the material becomes brittle. Beryllium teaches that plasma friendliness is not enough if toxicity, erosion, and fuel retention become too difficult. Together they show why the wall problem is so stubborn. The ideal wall must be both strong and clean, both heat-resistant and low-risk, both durable and replaceable, both close to the plasma and not too involved with it. It must be present enough to protect the machine and invisible enough not to disturb the star. And because no solid material has yet stepped forward as the perfect answer, researchers continue to look beyond the obvious. They look at coatings that can condition the surface. They look at boron, which can help tame impurities and improve plasma behavior, though it may wear away. They look at lithium, not only as part of the tritium breeding story, but as a possible surface that interacts with plasma in unusual and useful ways. They even consider liquid walls, where the surface might flow, renew itself, and carry heat differently from a solid tile. These ideas sound strange at first, but fusion has already taken us to strange places. Once you're trying to bottle a star with magnets, a flowing metal wall begins to seem less unreasonable than it should. The search for a wall that can survive is therefore not finished with tungsten and beryllium. They are important landmarks, not the end of the road. They show what is possible and what remains painful. They remind us that the barrier between fusion fire and the world cannot be chosen from a simple list of strong materials. It must be designed as part of the plasma itself, part of the fuel cycle, part of the heat engine, part of the maintenance system, and part of the future power plant. The wall is not merely where the reactor stops, it is where the reactor works hardest to remain itself. And as the search moves toward boron, lithium, and stranger surface chemistry, the boundary between wall and fuel, between protection and performance, begins to blur in a new and fascinating way. After tungsten and beryllium, the search for a fusion wall begins to feel less like choosing a single heroic material and more like learning how to manage the strange chemistry of an artificial star. The wall is not just a shield, it is a surface the plasma sees. It is a place where particles land, atoms are released, fuel is trapped or returned, impurities are absorbed or created, and tiny chemical choices can shape the behavior of something hotter than the sun. This is where boron and lithium enter the story, not as simple replacements for the solid wall, but as reminders that the boundary around plasma is not only a matter of strength, it is also a matter of chemistry. That may sound a little surprising. Fusion feels like a nuclear story. It belongs to the realm of plasma, magnets, neutrons, and stellar temperatures. Chemistry feels more familiar, closer to kitchens, batteries, cleaning products, and the odd smell of a new appliance warming up for the first time. But at the edge of a fusion plasma, chemistry matters deeply. The plasma does not float in perfect isolation. Its edge interacts with the chamber surfaces. Atoms can move from wall to plasma, from plasma to wall, and from one surface to another. Even a very thin layer on the wall can change how the plasma behaves. A coating only a tiny fraction of a human hair in thickness can help decide whether the plasma stays cleaner, hotter, and more stable. Boron is one of the materials that shows this clearly. It is not usually imagined as the main structural wall of a fusion reactor. It is not there to be the thick, load-bearing hero that stands in front of every neutron and heat pulse. Instead, boron is often used as a coating, a way of conditioning the inner surfaces of a plasma chamber. This process is sometimes called boronization. The idea is to place a thin, boron-rich film on the wall so that the plasma sees a more helpful surface. It is a little like preparing a pan before cooking, except the pan is the inside of a fusion machine and the meal is a swirling ring of charged particles, hot enough to make ordinary cookware reconsider its life choices. One reason boron is useful is that it can help control impurities, especially oxygen. Oxygen in the plasma can be troublesome because it radiates energy away. In a fusion machine, every unwanted radiator is a thief of heat. The plasma needs to stay hot, and impurities that carry energy away can make that harder. Boron has a talent for binding with oxygen and other impurities at the surface, reducing how much of them enter the plasma. When the walls are coated with boron, the plasma can become cleaner. Cleaner plasma often means better confinement, lower radiation losses from unwanted atoms, and improved performance. This sounds simple and almost too neat. Coat the wall, clean the plasma, continue toward unlimited energy, perhaps with a small break for tea. But boron coatings come with their own complications. A coating is not permanent. Plasma exposure wears it away. Particles strike it. Heat changes it. Atoms are sputtered from it. Deposits form elsewhere. Over time, the boron layer becomes thinner, patchier, and less effective. Then the machine may need to be conditioned again. In experimental reactors, this can be done as part of operation. In a future power plant, repeated wall conditioning would have to fit into a larger schedule of reliability, fuel management, and maintenance. A helpful coating is helpful only if it can be maintained without becoming a nuisance. Boron also illustrates something important about plasma-facing surfaces. Sometimes the best surface is not the bulk material underneath. A wall may be made from tungsten, steel, or another structural material, while the plasma actually interacts with a thin modified layer. That layer can change the chemical behavior of the edge, reduce impurities, and improve plasma conditions. The wall becomes more like a carefully prepared interface than a simple slab. It is not only what the wall is made of, but what the topmost atoms are doing today, after yesterday's plasma exposure, after the last conditioning cycle, after the previous burst of heat. In fusion, even the surface has a memory. There are also questions about fuel retention. Boron-rich films can trap hydrogen isotopes under some conditions. If those isotopes include tritium, that matters. Tritium is valuable, radioactive, and must be carefully accounted for. A coating that improves plasma behavior but stores too much fuel could create another problem. As always, fusion refuses to hand over a free advantage. You solve one difficulty, and another one quietly takes a seat nearby. Still, boron remains attractive because it can make a plasma behave better. In fusion, that is not a small gift. A cleaner plasma may require less heating power. It may radiate less energy from unwanted impurities. It may be easier to control. It may reduce the amount of damaging interaction between plasma and wall. Boron does not build the whole cage, but it can make the cage more acceptable to the star inside it. That is a subtle role, but subtle roles can be decisive. Lithium is stranger still. Most people know lithium from batteries. It is the light metal associated with phones, laptops, electric cars, and the anxious modern ritual of watching a battery percentage fall at exactly the wrong time. But in fusion, lithium has a very different set of meanings. It is not only a metal, it is a possible plasma-facing material, a coolant candidate in some designs, and most importantly a key ingredient in the breeding of tritium fuel. Lithium sits at the crossing point between wall chemistry, fuel supply, and reactor design. It is not simply one material option among many. It is woven into the question of whether a deuterium and tritium fusion power plant can feed itself. At the plasma-facing surface, lithium has some unusual attractions. Like boron and beryllium, it is a light element. If small amounts of lithium enter the plasma, they are generally less damaging than heavy impurities such as tungsten. Lithium can also absorb hydrogen isotopes. This changes how the plasma edge behaves. Normally, when plasma particles strike the wall, many of them can return to the plasma as neutral atoms or molecules. This returning fuel from the wall is called recycling. High recycling can cool the edge and affect plasma stability. Lithium surfaces can reduce recycling by holding onto hydrogen isotopes more strongly. That can make the plasma edge quieter and hotter in useful ways. In experiments, lithium coatings and lithium-conditioned walls have sometimes improved plasma performance. The plasma can become cleaner, edge behavior can change, and confinement can improve. It is as if the wall, instead of bouncing particles back into the plasma like an impatient tennis partner, begins absorbing some of them and calming the edge. A calmer edge can help the core remain hot. The core, in turn, is where fusion wants to happen, so a surface only a few atoms deep can influence the behavior of the entire plasma. Once again, the boundary becomes part of the star. Liquid lithium takes the idea even further. A solid wall remembers damage. It cracks, erodes, roughens, and accumulates defects. A liquid surface, in principle, can renew itself. If particles strike it, the surface can flow. If heat lands on it, the liquid can carry heat away. If the top layer is damaged, new liquid can replace it. This sounds almost magical in the context of fusion materials. Instead of a wall that slowly collects scars, imagine a wall that moves, refreshes, and heals in a limited physical sense. Not alive, not conscious, not a silver puddle from a science fiction film, but a flowing metal surface that does not crack the way a solid cracks. There is a deep appeal to this. A liquid metal surface might handle intense particle bombardment without suffering the same kind of permanent surface erosion. It could absorb fuel particles. It could be circulated, cleaned, cooled, and replaced. It might reduce the release of heavy impurities. It might help protect solid structures behind it. For a machine that wants to operate for long periods beside an artificial star, a renewable surface is a very tempting idea. But lithium does not make the problem disappear. It changes the problem into a different shape. Lithium is chemically reactive. It does not behave like a polite puddle of water. It reacts with air, moisture, and other substances. Handling it safely requires care. A power plant using liquid lithium would need systems to contain it, pump it, cool it, monitor it, and prevent unwanted reactions. If there is a leak, the concern is not only that material has escaped, but that a reactive metal may meet something it should not meet. A fusion reactor already has enough dramatic relationships inside it. Lithium adds another. Liquid metals also interact with magnetic fields in complicated ways. A conducting liquid moving through a magnetic field can experience forces that resist its motion and change how it flows. This is called magnetohydrodynamics, though we can simply think of it as the problem of moving an electrically conducting liquid through a world of powerful magnets. The magnets that confine the plasma do not politely ignore the lithium. The flowing metal feels their presence. Pumping it may become harder. Flow patterns may change. Turbulence may be suppressed or altered. Heat removal may be affected. A liquid wall may sound soft and forgiving, but inside a fusion reactor it becomes part of an electromagnetic puzzle. There is also evaporation. Lithium has a vapor pressure that can matter at high temperatures. If too much lithium evaporates into the plasma, it can affect plasma performance. A little lithium may be useful. Too much can become an impurity problem. The surface temperature must be controlled. The flow must be managed. The amount of lithium entering the plasma must stay within acceptable limits. A liquid surface that helps the plasma at one level may disturb it at another. Fusion is very fond of narrow acceptable ranges, which is one reason it has not yet become a household appliance. Lithium can also retain tritium. Because lithium absorbs hydrogen isotopes, it can hold tritium in the surface or in the circulating liquid. This could be useful for fuel handling in some ways, but it also raises safety and accounting concerns. Tritium must be recovered, processed, and returned to the fuel cycle. A lithium system that absorbs tritium must be designed so the tritium does not simply vanish into the metal inventory. In a working reactor, fuel is not a vague concept. It is measured, tracked, recovered, and regulated. If the wall becomes part of the fuel reservoir, the wall also becomes part of the fuel management system. That is one of the reasons lithium is so fascinating. It blurs categories. Is it a wall material? Is it a fuel breeding material? Is it a coolant? Is it a tritium storage medium? Is it a plasma control tool? Depending on the design, it can be several of these at once. This can be powerful because one material may perform many useful functions. It can also be dangerous because when one material does many jobs, a problem in one role can affect the others. If lithium is both near the plasma and part of the fuel cycle, then plasma-facing behavior and tritium handling become linked. If it is also flowing through magnetic fields, then fluid mechanics joins the discussion. If it is hot and reactive, chemistry raises its hand too. This is the strange chemistry of containing a star. You're not merely asking which material can stand the heat. You're asking how a surface behaves as a chemical partner to plasma. Does it absorb impurities? Does it release unwanted atoms? Does it trap fuel? Does it reduce recycling? Does it evaporate? Does it form dust? Does it flow? Does it react? Does it breed fuel? Does it help the plasma stay clean or quietly introduce new problems that only appear after many hours of operation? Boron and lithium both show that the wall is not only defensive, it can be active, it can change the plasma, it can prepare the edge, it can control impurities, it can influence confinement. A reactor wall is not simply the last thing the plasma hits, it is part of the plasma system. This is a subtle shift in thinking. In ordinary engineering, a wall is often separate from what it contains. A bottle holds water, but the glass is not meant to participate much in the water's behaviour. In fusion, the bottle and the contents are constantly negotiating. The plasma is affected by the wall, and the wall is changed by the plasma. The boundary is alive with exchange. There is another way to think about it. A fusion reactor must hold something that cannot be held by touching. Magnetic fields do the main work of confinement, but the material surfaces still shape the environment. The plasma floats in the centre, but it knows what the walls are made of. It knows through impurities, recycling, radiation, edge cooling, and surface interactions. If the wall is poorly chosen, the plasma becomes harder to keep hot. If the wall is well conditioned, the plasma may settle into better performance. So the wall becomes almost like the weather around the star. Invisible in the core at first glance, but influential everywhere. Boron is like a quiet housekeeper, binding troublesome impurities and making the chamber cleaner for a time. Lithium is more like a strange caretaker, absorbing fuel particles, calming recycling, possibly flowing and renewing itself, while also carrying the complications of reactivity and tritium management. Neither one is a complete answer. Both are tools. Both are imperfect. Both remind us that fusion is not solved by brute strength alone. It is tempting to imagine that the final fusion reactor wall will be made from one perfect substance, a material with a name that sounds futuristic, and a personality that can only be described as heroic. But the real answer may be a layered, managed, changing surface. A tungsten structure in one place, a boron coating at certain times, a lithium system in another region, advanced steels behind the wall, ceramic breeders deeper in the blanket, coolants moving through channels, sensors watching, robots replacing, and plasma control systems adjusting conditions moment by moment. The cage for the star may not be a cage at all in the simple sense. It may be a carefully choreographed borderland. In that borderland, the difference between solid and liquid matters. Solids can be shaped precisely. Liquids can renew. Solids can crack. Liquids can splash, evaporate, and flow unpredictably. Solids can be joined to cooling systems. Liquids can carry heat but may fight the magnetic field as they move. Solids store damage. Liquids store chemical complications. There is no escape from trade-offs. There is only the question of which trade-offs can be understood, controlled, and made acceptable for a working power plant. Lithium also brings us closer to the fuel problem that waits behind the wall. In deuterium and tritium fusion, tritium is both essential and scarce. Every serious design for a future reactor must answer where the tritium comes from. Lithium is central because neutrons from the fusion reaction can interact with lithium to produce tritium. This is why the material surrounding the plasma is not merely a shield. It is a breeding blanket, a system designed to capture neutrons, produce heat, and create new fuel. In that sense, lithium is not just a helpful surface material, it is part of the reactor's ability to continue operating. That is where the chemistry of the wall begins to merge with the economy of the fuel cycle. A reactor cannot simply burn tritium and hope more appears. It must produce enough to replace what it uses, recover it efficiently, and manage losses. If lithium is in the wall, the blanket, or a flowing system, then it becomes part of a larger loop. Neutrons leave the plasma. Lithium catches some of their story. Tritium is born, extracted, processed, and sent back as fuel. The reactor begins to look less like a furnace and more like a living industrial metabolism. Fuel enters, fusion happens, energy leaves. New fuel is bred, materials change, and the cycle continues if every part does its job. Boron and lithium therefore teach a deeper lesson than material choice. They show that containing a star is not just about resisting it. Sometimes it is about cooperating with it. A surface can clean the plasma. A liquid can absorb particles. A blanket can turn escaping neutrons into new fuel. The wall is not only a barrier against damage, it can become an active system that shapes, feeds, and stabilizes the reaction. But cooperation with a star is never simple. Boron wears away, lithium reacts, coatings need renewal, liquids need control, tritium must be tracked. Magnetic fields complicate flow, heat still has to be removed. Neutrons still damage whatever lies behind. The perfect surface remains out of reach, but each imperfect surface teaches engineers how the plasma wants to behave and how matter might survive beside it. So as we move past the surface chemistry and toward the deeper layers of the reactor, the question changes. It is no longer only what can face the plasma, it becomes what can use what the plasma sends outward. The neutrons that damage the wall are also the key to making new tritium. The lithium that complicates the surface is also the element that may feed the reactor's future. The blanket behind the wall is not simply armour, it is a factory, a heat collector, and a fuel source wrapped around the artificial star. And to understand why fusion energy depends on it, we have to follow the escaping neutron beyond the first surface, into the region where the reactor must learn to make its own fuel, while surviving the very particles that make that possible. Tritium is one of the quietest problems in the loud dream of fusion. It does not glow in the imagination the way plasma does. It does not have the grandeur of huge magnets, or the drama of a wall facing heat from an artificial star. It is just a form of hydrogen, tiny, rare, radioactive, and absolutely central to the kind of fusion power plant scientists most often hope to build first. And yet, without tritium, the whole promise begins to wobble. You can have the magnets, you can have the chamber, you can have the wall, the heating systems, the cooling loops, the patient engineers, and the diagrams with reassuring arrows. But if the fuel cannot be supplied, recycled, and reborn inside the reactor itself, the star in the bottle has no steady way to keep burning. This is one of fusion's most important hidden truths. The fuel problem is not only about getting fuel at the beginning, it is about making fuel while the machine runs. Fusion on Earth is often imagined as using hydrogen, because hydrogen is simple and abundant. That is true in the broad sense, but the details matter. The most practical fuel combination for early power-producing fusion is not ordinary hydrogen by itself. It uses two heavier forms of hydrogen, deuterium and tritium. Deuterium is fairly accessible. It exists naturally in water, in small amounts, and can be separated from it. The oceans contain enough deuterium to make the idea feel wonderfully generous. Tritium is different. Tritium is unstable. It decays over time. It is not found in large natural reserves waiting patiently underground. It has to be produced. That makes tritium both fuel and problem. It is the ingredient that helps fusion happen at temperatures and conditions more reachable than many other fuel choices, but it is also rare enough that a future fleet of fusion reactors could not simply depend on existing supplies. If fusion power plants are to operate for years, decades, and eventually perhaps all over the world, they must learn to make their own tritium. The reactor must become a kind of fuel garden, growing what it consumes, quietly and continuously, in the layers surrounding the plasma. This is where the breeding blanket comes in. The name sounds almost gentle, even cozy. A blanket. Something warm, protective, wrapped around the glowing centre. In one sense, the word is fitting. The blanket surrounds the plasma chamber, sitting behind the first wall, ready to absorb what escapes from the fusion reaction. But this is not a blanket in the soft bedtime sense. It is a dense, engineered region filled with materials chosen to slow neutrons, capture heat, protect the rest of the machine, and produce tritium from lithium. It is one of the most important systems in a future fusion power plant. Without it, the reactor may produce fusion energy for a while, but it cannot become self-sufficient in fuel. To understand why, we return to the neutron. In the fusion reaction between deuterium and tritium, much of the energy leaves as a fast neutron. Because the neutron has no electric charge, the magnetic fields cannot hold it. It slips away from the plasma and travels outward, passing through the edge, through the first wall and into the blanket beyond. Earlier we saw this neutron as a source of damage, a tiny invisible hammer striking atoms from their places, that is still true. But in the breeding blanket, the neutron is also useful. It is the messenger carrying energy away from the plasma. It is the trigger that can help create new tritium. It is both trouble and treasure depending on what catches it. Lithium is the key. When neutrons interact with lithium in the blanket, tritium can be produced. That is the basic idea of tritium breeding. The reactor consumes tritium in the plasma, then uses the escaping neutrons to make more tritium in the surrounding blanket. The new tritium must then be extracted, purified, measured, and returned to the fuel system. If the cycle works well enough, the reactor can keep feeding itself. If it does not, the reactor becomes dependent on an outside supply of tritium that may be too limited for large-scale power. This sounds elegant, almost circular. The plasma produces neutrons. The neutrons enter lithium. Lithium produces tritium. Tritium goes back into the plasma. The reactor makes heat and replaces its own fuel. A neat little loop, like a candle that somehow manufactures more wax while it burns. But as usual, fusion does not allow the elegant version to remain simple for long. The first difficulty is that not every neutron will produce tritium. Some neutrons are lost. Some are absorbed in structural materials. Some are scattered. Some are captured in places where they do not help the fuel cycle. Some may leak into shielding. The blanket must be designed so that enough neutrons reach lithium and produce enough tritium to replace what the reactor burns, plus extra to cover losses, processing delays, decay, and inventory needs. In other words, the reactor cannot merely break even in a vague sense. It must breed enough tritium reliably, with margin, while also doing all its other jobs. That margin matters because tritium is slippery in the engineering sense. It can move through materials, it can be trapped in surfaces, it can dissolve into liquids, it can bind with other substances, it can leak if systems are not carefully designed. Since tritium is radioactive, even though its radiation is relatively easy to shield compared with many other forms, it must be handled with great care. A power plant must know where its tritium is. In the fuel system, in the plasma exhaust, in the blanket, in processing equipment, in wall deposits, in maintenance components, in storage. Tritium accounting becomes part of reactor operation. The fuel is not only burned, it is followed. A breeding blanket therefore has to be more than a block of lithium-rich material. It must allow tritium to be removed. If tritium is made but stays trapped inside the blanket, it cannot refuel the plasma. The blanket would become a fuel prison instead of a fuel factory. So engineers must think about tritium extraction from the beginning. The breeder material may be a solid ceramic containing lithium, or a liquid metal mixture, or a molten salt in some concepts. Each choice changes how tritium is produced, how it moves, how it is recovered, and what other problems appear. Solid breeder blankets can use lithium containing ceramic materials. These materials can sit inside modules behind the first wall, exposed to neutrons while cooling systems remove heat. Solid ceramics have advantages. They can be stable at high temperatures, shaped into pebbles or blocks, and arranged within structures. But they also have challenges. Tritium produced inside the solid must diffuse out. The ceramic may swell, crack, or change under radiation. Heat must be removed without damaging the material. The packing of small breeder pebbles must remain reliable under thermal cycling and radiation. Even something as innocent as the way small particles settle, crack, or press against each other can become important when the blanket has to work for years. Liquid breeder blankets offer a different path. A liquid containing lithium can flow through the blanket, absorb neutron energy, produce tritium, and carry both heat and tritium toward extraction systems. This has a certain appeal. A flowing breeder can move what it produces. It may simplify some aspects of tritium recovery and heat removal. But liquid breeders bring their own demanding personality. If the liquid is electrically conducting and moves through strong magnetic fields, the flow can be slowed or reshaped by electromagnetic forces. Pumping becomes harder. Heat transfer changes. The liquid may corrode structural materials, it may react chemically with air or water. It must be contained perfectly enough for a power plant, not just admired in a laboratory loop. There are also concepts using molten salts, which may contain lithium and allow tritium breeding with different chemical behaviour. Molten salts can operate at high temperatures and may have attractive heat transfer properties, but they also raise questions about corrosion, chemistry control, tritium extraction, and compatibility with materials. In fusion, every blanket concept is like a guest arriving with useful skills and a surprising amount of luggage. Then there are neutron multipliers. Some blanket designs include materials that help increase the number of useful neutrons, because breeding enough tritium is not easy. Certain materials, such as beryllium or lead, can interact with incoming neutrons in ways that produce additional neutrons. These extra neutrons can then help produce more tritium in lithium. This sounds like a clever trick, and it is, but it also adds more material challenges. Beryllium is toxic and changes under radiation. Lead-based liquids can be heavy, corrosive, and complicated to handle. The blanket becomes a carefully balanced mixture of breeder, multiplier, structure, coolant, and extraction systems, each with its own behaviour under heat and radiation. The breeding blanket must also capture energy. Remember, the neutron carries much of the fusion energy out of the plasma. When neutrons slow down and are absorbed in the blanket, their energy becomes heat. That heat must be removed by a coolant and eventually used to make electricity. So the blanket is both fuel factory and heat exchanger. It must breed tritium and deliver usable heat at temperatures high enough for efficient power conversion. If it runs too cool, efficiency suffers. If it runs too hot, materials may fail. If heat removal is uneven, local hotspots can develop. If coolant channels crack or corrode, the entire module may be compromised. The blanket also protects the magnets. Behind the first wall and blanket are some of the most expensive and sensitive parts of the reactor, including superconducting magnets. These magnets need protection from neutron radiation and heat. If too many neutrons reach them, they can damage the superconducting materials, insulation, and support structures. The blanket and shielding must reduce that radiation enough to preserve the magnets over the reactor's lifetime. So the blanket must let neutrons do useful work in the breeding region, but not let too much damage reach what lies beyond. It is less like a simple shield and more like a selective maze for particles, guiding their effects toward fuel production and heat capture while protecting the rest of the machine. This is why blanket design is so difficult. It must be thick enough and clever enough to capture neutrons and breed tritium, but not so bulky that the reactor becomes enormous. It must allow cooling, but coolant channels reduce space for breeder material. It must include structural materials, but structural materials can absorb neutrons that might otherwise breed tritium. It must include sensors and support systems, but every added component changes the neutron economy. It must be replaceable, because radiation damage will eventually degrade it, but replacement requires remote maintenance in a radioactive environment. A breeding blanket is a compromise wrapped around another compromise, sitting behind a wall that is already compromising with plasma. The phrase "fuel that must be reborn" is not poetic exaggeration. Tritium really must be regenerated. A power plant may have some initial tritium inventory to start operation, but after that, it must close the loop. This is sometimes called the tritium fuel cycle, and it includes more than breeding. Tritium and deuterium must be injected into the plasma. Unburned fuel must be pumped out of the exhaust. Helium ash must be separated. Tritium must be recovered from the blanket. Contaminants must be removed. The fuel must be stored safely and sent back into the machine. The cycle must be efficient because only a fraction of the fuel passing through the plasma burns in each pass. Much of it must be recycled. This makes the reactor feel almost biological, though it is entirely mechanical and physical. It breathes in fuel. It burns a small part of it. It exhales ash and unburned fuel. It absorbs neutrons in a surrounding organ made of lithium-rich material. It creates new tritium and returns it to the bloodstream of the machine. The metaphor is imperfect, of course, but it helps show why fusion power is not simply a hot plasma in a chamber. It is a circulating system. Fuel, heat, particles, radiation, and materials are all moving through loops. Tritium handling also shapes safety. Since tritium can combine with oxygen and form tritiated water, and since water can move through biological systems, releases must be prevented and monitored. Fusion plants would need containment barriers, detritiation systems, careful ventilation, leak detection, and strict operating procedures. The amount of tritium on site must be controlled. Components that trap tritium must be managed. Maintenance systems must account for contamination. The goal is not to pretend tritium is harmless. The goal is to design the plant so its hazards are understood and contained. There is a strange contrast here. Fusion is often promoted as having abundant fuel, and in the case of deuterium that is broadly true. But tritium is not abundant. The abundance promise depends on making tritium from lithium. Lithium is much more available than tritium, but it is still a material that must be mined, processed, purified, and placed into blankets. Different forms of lithium matter too. Natural lithium contains different isotopes, and one of them is especially useful for tritium breeding. Enriching or managing lithium composition may become part of the industrial story. So even a future fusion economy has supply chains. They may be far smaller and cleaner than fossil fuel supply chains, but they do not vanish into pure starlight. A future reactor must also prove that breeding works in practice, not just in calculation. It is one thing to model neutrons moving through blanket materials. It is another to build a full system that breeds enough tritium while surviving heat, radiation, corrosion, stress, and time. Test blanket modules are designed to study these questions in experimental fusion devices. They are like small trial pieces of future power plant blankets, exposed to relevant conditions so engineers can learn how breeder materials, coolants, structures, and tritium extraction systems behave. This is a necessary step because the breeding blanket cannot be fully trusted until it has faced something close to the real environment. And here we return to the first wall. The blanket sits behind it, but the two are connected. The first wall must allow neutrons through into the blanket while surviving their passage. It must transfer heat. It must protect the blanket structure from plasma-facing damage. It must not absorb too many neutrons that are needed for tritium production. It must not become so thick or so complicated that breeding suffers. The wall and blanket are not separate characters in separate stories. They are parts of the same boundary system. The first wall receives the plasma's direct punishment. The blanket receives the neutron's deeper message. Together they decide whether fusion energy can be captured and fuel can be reborn. This is why the final barrier to fusion is not only the surface facing the plasma, it is the entire zone where the artificial star meets the machine. The plasma produces energy. The neutrons carry it outward. The wall survives the first contact. The blanket catches the neutrons, turns their energy into heat, and tries to make tritium. The coolant carries heat away. The fuel system recovers what is made. The reactor feeds itself again. If one link fails, the circle breaks. There is something quietly demanding about this circle. It does not allow fusion to be just a spectacular event. It must become a disciplined process. A pulse of fusion in a laboratory is a triumph of plasma physics. A reactor that breeds its own tritium is a triumph of systems engineering. The difference is enormous. It is the difference between lighting a brilliant flame and running a civilization on the heat. Tritium breeding also affects how we think about time. A reactor may begin with a supply of tritium, but it must plan for the future from the moment it starts. The tritium born today may become the fuel burned tomorrow. The blanket slowly accumulates radiation damage while producing the fuel that justifies its existence. Components age while sustaining the cycle. The machine is always living slightly ahead of itself, using present neutrons to prepare future fuel. That is a beautiful idea, but also a demanding one. Energy abundance depends on a careful loop that never gets too careless. So when someone says fusion fuel could come from water and lithium, the statement is both hopeful and incomplete. Deuterium from water is only the first half of the story. Lithium must be arranged around the plasma in a way that catches neutrons and breeds tritium. Tritium must be extracted and recycled. The blanket must endure. The wall must survive. The neutrons must be useful without being too destructive. The fuel must be reborn at the same pace the star consumes it, with enough extra to cover losses and keep the plant alive. This may be the deepest reason fusion feels almost impossible and still irresistible. It is not enough to make a tiny sun. You must build a world around it. A world that catches its invisible particles, harvests its heat, makes its fuel, protects its magnets, watches its chemistry and repairs its own wounded surfaces. A fusion reactor is not a bottle. It is a complete artificial environment for a star that cannot exist naturally on Earth. And as we come closer to the end of this journey, the shape of the challenge becomes clearer. The plasma must be hotter than the sun. The magnetic cage must keep it suspended. The first wall must stand near it without poisoning it. The materials must endure heat and neutrons. Boron and lithium must help manage the strange chemistry of the edge. The breeding blanket must turn escaping neutrons into new tritium. Every part of the machine must cooperate because none of them can solve fusion alone. The fuel that must be reborn is therefore more than a technical detail. It is a symbol of the whole fusion challenge. Fusion is not simply about release. It is about return. Energy leaves the plasma, heat enters the blanket, tritium is made, fuel returns, and the cycle begins again. If that cycle can be made steady, safe, and economical, then the artificial star becomes more than a laboratory wonder. It becomes a power source. But if the cycle cannot be closed, then fusion remains a brilliant fire that has not yet learned how to feed itself. So the final question is not only whether humans can make fusion happen. We already know fusion can happen. The harder question is whether we can make it last as a practical machine, surrounded by materials that survive, blankets that breed, systems that recycle, and walls that do not surrender too quickly. The future of fusion depends on all of this at once, and that brings us back to the title of the whole dream, the final barrier to infinite energy, where the promise of the star and the patience of matter meet in the narrow space between fire and the world. The final barrier to infinite energy is not a door with a bright warning light above it. It is not a single switch waiting for someone to press it. It is not one last secret equation hidden on a blackboard, waiting for a tired physicist to notice the missing piece after midnight. The final barrier is quieter than that, and in some ways more stubborn. It is the place where the dream of fusion has to stop being a dream and become a machine. It is the boundary between a tiny artificial star and the ordinary world that wants useful electricity, safe operation, predictable costs, and a power plant that can wake up tomorrow and do the same thing again. That is the hard part. Not making fusion happen for a brief shining moment. Not proving that hydrogen nuclei can join and release energy. The universe has been proving that every second for billions of years. Stars are already doing the physics with no applause and no maintenance schedule. The hard part is building a human-made system that can make fusion happen steadily, collect its energy, protect itself from the damage, breed its fuel, and keep working long enough to matter. A star does not have to be economical. A star does not need replacement parts. A star does not have to pass safety inspections or make electricity at a stable price. A star simply exists. A fusion reactor has to perform, and that performance depends on the barrier. All through this journey we have moved closer and closer to that boundary. We began with the promise, the almost impossible attraction of energy from the same process that lights the sun. We saw why fusion is so tempting, because it offers dense power without ordinary combustion, without the smoke and carbon of fossil fuels, and with fuel possibilities that seem, at first glance, almost too generous. Then we moved into the plasma itself, that restless charged state of matter hotter than the sun, held not by a normal container, but by magnetic fields shaped with extraordinary precision. We saw that the plasma is both the source of the dream and the source of the danger. It gives energy, but it also sends heat, particles, radiation, and neutrons outward. Then we reached the first wall, the first solid surface between the plasma and the rest of the reactor. It looked at first like a simple shield, but it quickly became something more complicated. It has to survive heat. It has to avoid poisoning the plasma with impurities. It has to face erosion, trapped fuel, surface changes, and the invisible violence of neutron damage. Behind it, the breeding blanket must catch what the plasma releases, turning neutron energy into heat, and using lithium to create new tritium. The reactor must not only burn fuel, it must make fuel. It must become a cycle. That is why the phrase infinite energy needs a gentle pause. Fusion is not infinite in the magical sense. It does not break the rules of nature. It does not create energy from nowhere. It still needs fuel, materials, maintenance, cooling, engineering, and time. But compared with the energy sources that have shaped human history, fusion feels almost endless because its fuel is so energy dense and because deuterium is so widely available. If tritium can be bred successfully from lithium, if the materials can survive, if the systems can close the loop, then fusion could give humanity an energy source with a scale that feels almost impossible from where we stand now. Not infinite like a fairy tale, but vast enough to change civilization. And yet, vast possibility does not remove the small difficulties. It magnifies them. A future fusion power plant might be large, powerful, and impressive from the outside, but its success may depend on the behavior of atoms in the wall. A little tungsten entering the plasma, a small crack growing in a heated surface, a coating wearing away, tritium hiding inside deposits, helium bubbles forming in metal, a coolant channel facing stress, a neutron changing the structure of a material deep inside a blanket module. These details sound tiny, almost invisible beside the grand promise of star power, but engineering often lives in tiny details. A bridge can fail because of a crack. A rocket can fail because of a seal. A reactor can fail because the surface closest to the plasma changes faster than expected. This is one of the humbling lessons of fusion. The biggest dream depends on the smallest tolerances. You can speak of powering cities, cleaning grids, desalinating oceans, and reducing the burden of carbon, but somewhere inside the machine a material still has to survive the next pulse, the next neutron, the next heat load, the next cycle of expansion and contraction. The future may depend on whether matter remains patient at the atomic scale. There is something almost funny about it. Humanity wants to bottle a star, and the star replies, "Very well, but how good are your tiles?" The answer is still being written. Tungsten stands as one of the great candidates, strong against heat, difficult to melt, resistant to erosion in many conditions, but dangerous if too much of it enters the plasma and vulnerable to brittleness under radiation. Beryllium offers lightness and useful plasma chemistry, but brings toxicity, erosion, and fuel retention concerns. Boron can help condition the wall and clean the plasma, but coatings wear away and must be renewed. Lithium can calm the plasma edge, absorb fuel particles, and help breed tritium, but it is reactive, difficult to handle, and complicated by magnetic fields and fuel accounting. None of these materials is the hero in a simple story. Each is a compromise, each is a tool, each solves part of the problem while creating another part that must be handled with equal care. That may sound discouraging, but it is also the normal shape of difficult progress. Airplanes were not made practical by one discovery. They needed engines, wings, control systems, materials, instruments, pilots, maintenance methods, and airports. Spaceflight was not achieved by knowing rockets could move. It needed guidance, heat shields, fuels, structures, life support, and a willingness to test everything until the machine stopped surprising people in dangerous ways. Fusion is following a similar path, but under conditions that are almost absurdly extreme. It asks many fields of human knowledge to cooperate. Plasma physics, nuclear physics, materials science, chemistry, robotics, cryogenics, heat transfer, control systems, safety engineering, and economics all have to sit at the same table and agree on a machine. The plasma physicist may want a wall that keeps impurities low. The materials scientist may want a wall that survives damage. The tritium engineer may want a blanket that breeds fuel efficiently and releases it quickly. The power engineer may want high temperatures for better efficiency. The safety expert may want low activation materials and limited tritium inventories. The maintenance engineer may want modules that robots can replace without heroic difficulty. The economist may want all of this to be affordable, and somewhere, quietly, the plasma continues to be plasma, with very little interest in committee meetings. This is why fusion is not just a physics problem, it is a systems problem. The star in the bottle is only the centre. Around it must be an entire artificial environment that lets the star exist without destroying its home. The magnets hold the charged particles. The wall catches what escapes. The blanket turns neutrons into heat and new fuel. The coolant carries heat away. The turbines or other systems convert heat into electricity. The tritium plant recovers, cleans, and returns fuel. The robots repair what radiation has made unsafe for human hands. The sensors watch every flow, temperature, impurity, crack, and leak. The whole thing must behave not as a single experiment, but as a working organism of machinery. And the barrier is where all those systems meet. If the wall fails, the plasma suffers. If the plasma misbehaves, the wall suffers. If neutrons are not captured well, the blanket cannot breed enough tritium. If the blanket absorbs too many neutrons in the wrong places, the fuel cycle suffers. If the materials activate too strongly, maintenance becomes harder. If tritium is retained too much in the wall, safety and fuel supply become harder. If heat cannot be removed efficiently, the power plant cannot run. Each problem is linked to the others. A fusion reactor is a web of consequences wrapped around a ring of starfire. So the final barrier is not simply a wall, it is the whole idea of controlled closeness. How close can human technology come to a star and remain orderly? How close can matter stand to nuclear fire and still keep its shape? How close can a machine come to the conditions of the sun and still be repaired on a weekday? That last part matters more than it sounds. A technology becomes civilization changing only when it can leave the heroic laboratory and enter routine life. It must become reliable enough to be ordinary. The dream of fusion is not a dramatic flash in a chamber. It is a quiet power station that keeps working while most people are thinking about dinner. There is a beautiful contrast in that. The inside would be extraordinary. Plasma hotter than the sun, magnetic fields stronger than almost anything in daily life, neutrons rushing outward, lithium breeding tritium, materials enduring damage that no kitchen, bridge or furnace would ever experience. Outside, perhaps, there would be buildings, cables, cooling systems, service roads, and people arriving for shifts with lunch in a bag. The extraordinary would be hidden inside the ordinary, doing the steady work of keeping homes warm and lights on. That is often the destiny of great technology. It becomes background. The first time humans captured electricity, it was a wonder. Now a light switch is so normal that we only notice electricity when it disappears. The first powered flights were miracles of wood, cloth, engines and courage. Now people complain when their flight is delayed by 20 minutes. If fusion succeeds, perhaps one day an artificial star will become just another part of the grid, noticed mostly by engineers, policymakers, and children on school trips who press their faces to a visitor centre window and ask if the star is really in there. It might be. Not a star in the full natural sense, of course. not a giant sphere of plasma held by gravity and shining across space. A controlled plasma, a carefully shaped reaction, a small and temporary star-like condition sustained by magnets, fuel systems and human design. But still, in its heart, the same deep principle. Light nuclei joining, energy released from the nucleus, a process older than Earth brought into a machine built by hands. And perhaps that is why fusion feels so powerful as an idea. It is not merely another energy technology, it is a reversal of scale. For almost all of history, the sun has been above us, unreachable, immense, the source of seasons, weather, food, warmth, and daylight. We built myths around it. We measured time by it. We rose when it rose and slept when it left. Fusion asks whether we can bring one small piece of that cosmic process down to Earth, not to worship it, not to fear it, but to use it carefully. That is a profound ambition. It deserves both excitement and humility. Humility is important because fusion has been promised many times. The dream has often moved faster than the machines. People have imagined fusion arriving just beyond the next decade, and then the next, and then the next. There has been progress, real progress, but the final system remains hard. It is easy to become impatient with fusion, to see it as a beautiful horizon that moves away as we walk. But another way to see it is this. Each decade has taught us more about what the barrier really is. At first, the question seemed to be whether fusion could happen in a controlled machine. Then it became whether plasma could be confined long enough. Then whether it could produce more energy in meaningful ways. Then whether a reactor could handle heat, breed fuel, survive neutron damage, and operate as a plant. The goal has not simply moved, it has become clearer. And clarity is progress, even when it reveals more difficulty. The closer we get to fusion, the less it looks like a single miracle, and the more it looks like a chain of mastered hardships. Better magnets, better plasma control, better diverters, better wall materials, better blankets, better tritium systems, better robotics, better models, better ways to test materials before a full power plant exists. Every improvement is a stone in the bridge. The bridge is long, but it is not imaginary. The final barrier to infinite energy may therefore be less like a locked gate and more like a landscape of heat, radiation, fuel cycles, materials, surfaces, and maintenance. You do not open it with one key, you cross it step by step. Each step must be solid enough to hold the next. A plasma record means little if the wall cannot survive. A strong wall means little if the blanket cannot breed tritium. A breeding blanket means little if tritium cannot be extracted and recycled. A beautiful reactor design means little if it cannot be maintained safely and economically. Fusion is the art of making every necessary success arrive in the same machine. And yet, despite all of that, the dream continues. It continues because the reward is too large to ignore, and because the physics itself is real. Fusion is not a fantasy process. It works in stars. It works in experiments. The question is not whether nature permits it. The question is whether human beings can build the cage, the blanket, the cooling system, the fuel loop, and the long-lasting materials that let it become useful. The universe has already shown us the fire. We are trying to invent the hearth. A hearth is a good image, because every age of energy has needed one. Early humans did not only discover fire, they learned to contain it with stone, ash, distance, and care. Later, furnaces needed brick and metal. Steam engines needed boilers strong enough to hold pressure. Nuclear fission needed vessels, control rods, shielding, and cooling systems. Every powerful energy source has required a boundary, a way to let energy serve without letting it escape destructively. Fusion is the same ancient lesson at the highest temperature we have ever tried to manage. The fire is new in scale, but the problem is old. How do you invite power into your home without letting it burn the house down? the first wall and breeding blanket of fusion's hearth. They are not glamorous compared with the glowing plasma, but they are the reason the plasma could matter. They are the place where stellar energy becomes heat we can use. They are where the fuel cycle closes. They are where the machine proves whether it is a scientific wonder or the beginning of an energy industry. The wall does not simply stand between fire and the world. It teaches the fire how to belong here. Maybe that is the real final barrier. Not heat alone, not neutrons alone, not tritium alone, not materials alone. It is belonging. Can a star process belong inside a human machine? Can something born in the cores of stars be made steady enough for a power grid? Can the wildness of plasma be turned into routine service? Can matter, arranged with enough intelligence, become the patient neighbour of fusion fire? The answer is not yet fully known. That is what makes the story alive. Scientists and engineers are still testing materials, refining plasma control, designing blankets, developing tritium systems, and imagining walls that can survive longer than today's best guesses. Some answers may come from better solids, some may come from flowing liquids, some may come from smarter plasma shaping that reduces the burden on surfaces, some may come from reactors designed for easier replacement rather than impossible permanence. The future may not choose one path, it may combine many. And if fusion finally does become practical, it may not arrive with a single thunderclap. It may arrive gradually through prototypes, demonstration plants, hard lessons, redesigned components, better materials, and the slow transformation of an impossible dream into an operating schedule. That is often how the future really enters the room. Not as a perfect revelation, but as a machine that works a little better than the last one, until one day it works well enough that people begin to build more. So when we think of the final barrier to infinite energy, we can picture that inner wall again. Not as a cold piece of metal, but as the narrow border between cosmic power and human need. On one side, plasma, hot, charged, unstable, luminous, trying to become useful. On the other side, magnets, structures, coolants, blankets, sensors, turbines, cities, homes, and the quiet, ordinary lives that energy makes possible. Between them, a surface that must survive. That surface is not just a material, it is a question. Can we make a cage clever enough for a star? For now, the question remains open, but not empty. Every experiment, every damaged sample, every improved coating, every better magnet, every new blanket design, every tritium study adds a little more to the answer. The artificial star has not yet become a common power source, but the outline of the challenge is sharper than ever. Fusion is no longer only a dream of heat, it is a dream of endurance, and perhaps that is a fitting place to rest. The universe is full of stars that burn because gravity holds them together. Here on Earth, if we want star power, we must hold it with knowledge, materials, and care. We must build the wall, renew the fuel, guide the plasma, and accept that the brightest promise may depend on the quietest surface. Infinite energy, or something close enough to feel like it, may not be waiting in the fire itself. It may be waiting in the barrier that finally learns how to live beside the fire. So as your thoughts begin to slow, imagine that hidden chamber one last time. Not as a place of danger, but as a place of careful balance. A ring of plasma suspended by invisible fields. A wall standing close, receiving heat but not surrendering. A blanket behind it catching neutrons and making fuel anew. A machine built around a star not to trap it forever, but to borrow its principle for a while and turn it gently into light. And if this quiet journey through fusion, plasma, walls and patient matter brought you a little calm, or gave you something interesting to carry into sleep, I would be grateful if you liked the video and subscribed. Somewhere between the stars above us and the machines we build below, physics keeps offering questions that are both enormous and strangely intimate. Tonight the question was how to hold a star. Tomorrow perhaps it will be something smaller, or stranger, or even more impossible. But for now, Wherever you are listening from and whatever time it is in your little corner of the world, let the reactors cool, let the magnets hum in the distance, and let the artificial star remain safely in its cage while you drift gently toward rest.